Hello everybody. In this lecture we want to talk about the optimization applications. So there are many applications that we need optimization techniques to find out what is the optimal decision for doing that. Let me give you a very simple example. Suppose you want to construct a bridge and you want to find out how you should do it. Definitely you want to do it in an optimal way. So the decision variables are some let me name some of these decision variables. So, for example, you want to know if you want to create a bridge between 2 points, how many piles are needed? What is the optimal distance between these 2 piles? And also how much cost is needed for doing that construction? How many workers do you need for doing that in a minimum time? And which materials you have to use in order to minimize the environmental undesired impacts, and so on and so on. Okay, so you can see here that there are several issues associated with each optimization problem. So those objective functions and decision variables are dependent on the application. So let me give you another example. Suppose you want to build an aircraft, okay, and also you want to know, for example, how much fuel does it need, what is the aerodynamic constraints that should be satisfied, how much material do you need, what is the cost of building such a huge object, okay, and what are the safety issues. So you want to decide in an optimal way to better use your resources, okay. So for this purpose, you need to know how to deal with different kind of constraint creation and how to find out what is the optimal decisions in this regard. Okay. So different optimization problems can be categorized into some categories. For example, single objective optimization. So in this type of optimization, you only have one objective function, and also you have a multiple number of constraints, okay? So this is one way of dealing with the optimization. The other way is, for example, you have multiple objective functions and you want to find out what is the optimal decision variables in order to not only satisfy the decision constraints, but also the objective functions are both optimized. They can be minimized or they can be maximized, okay? And sometimes the objective function is inside the constraint. So you can see here the objective function 2 is inside the constraint. For example, let's say we want to maximize OF1 and we have an additional constraint saying that OF2 should be, for example, less than something or bigger than something, okay? So this is called multi-level optimization. So at the upper level we have some objectives, and at the lower level we have other objectives. And for each type of optimizations, we need to know how to deal with them. Okay, that's it very much. Python installation. This is the beginning of using this course. So first of all, you have to turn on your PC or laptop, and then go and Google the Anaconda, and then go to the part that has the installation files. So in the Windows it has 2 versions, 64-bit and 32-bit, and also in the Mac operation system and the Linux as well. So choose the right platform and download the appropriate version and install it on your machine. Okay, once the Anaconda is installed, then you can easily use the Python editor and also the Pyomo package and so on and so on. So this is the way I recommend start this course, because it's much easier and it will result in a less hassle kind of programming at the beginning. So but I should say that if you want to use any other platform like PyCharm or any other platform for doing editing your Python codes, feel free to do that. Okay, so once you finish installation of Anaconda, you have to go to the Home tab, and then launch the notebook, a Jupyter notebook, and it will start like this. You can go to the file, new notebook, Python 3, and then a new page will open, and you can start your coding. Okay, so and the other important question is, how can I install the Pyomo? So this is really easy. I show you how to do it. So go open your Google and then type Pyomo installation Conda, and the first link that appears here is giving you the answer. So you go to that link, and it gives you the command for doing the installation of the Pyomo. Copy that piece, go back to your Anaconda editor, and then go to the environment, not the home, the second tab, environment. Go to the base root, open terminal. Once your terminal is open, paste the command here, okay? And that will install the Pyomo package. So what solver I should use? You can use IPOP, GLPK, or any other solver that you have the license for it, okay? So search the IPOP the same way and copy the installation piece here and put it in the terminal and install it, okay? You can also install the GLPK solver and do the same, okay? And that's it for the installation. Thank you very much. So visualization in Python. So in this course, when we solve the optimization problem, I usually prefer to show you how to visualize the decision variables and also the objective functions. So for this purpose, there are some multiple packages in Python, like Seaborn, like ggplot, like bokeh, like pygal, and also plotlib and geoplotlib, gleam, missing no, ladder, and also the main one that I'm going to use it throughout this course is matplotlib. So we can use these tools to visualize our decision variables and also the objective functions and how they are changing with the decision maker, okay? And also, so we don't have any insist of using any specific package in Python, but for simplicity I have chosen the matplotlib, but you feel free to change that part of the code and do the visualization by your own creativity. So in order to learn more about the matplotlib, you can Google it, and there is a website called matplotlib.org, and it has a gallery. It has multiples of solved examples, so you can easily use them. You don't need to memorize everything, of course, but if you need anything, you can go to the gallery and find out which of these examples are much closer to what you exactly need. So this is an example. For example, you need to import matplotlib.pyplot as plt and import numpy as np. And for example, in this plot, you can see there are some random shapes are scattered in the plane, okay? So this is the application of a scatter plots, and you finally show that plot to your audience, okay? So that's the way you visualize the things in Python. This is very simple, but you need to practice as well. Thank you very much. So the question is, what are the Pyomo elements and what exactly Pyomo is doing for us? So to answer this question, you should know that it's you who writes down the problem description. So you have to mathematically model your problem. Suppose you are about to solve the diet problem, and you want to have some specific amount of proteins, carbohydrates, and also, for example, fats in your diet, okay? And you need to be able to choose how much, for example, rice I should take, how much meat I should take, how much bread I should eat every day, okay? So this is the typical diet optimization problem in a way that not only I'm paying the minimum amount of money, but also I supply them the required amount of vitamins, proteins, and different things to my body. So you have to somehow mathematically formulate your problem. So Pyomo doesn't understand the physical nature of that problem. It doesn't really understand what is the physics or what is the diet or what is whatever. So it only understands the mathematics. So you have to mathematically formulate your problem and then pass it to the solver. So I should say that Pyomo is not solving your problem. These are the solvers who solve your problem. This means that Pyomo is only acting as a translator, so it will translate your problems for the developed solver, which is at the back of the problem. So for this reason, we have to know what are the components of each Pyomo code. So first of all, the model. The model is the most important thing in Pyomo. You have to create your model. You have to build your model based on the actual problem you are trying to solve. Okay, so the models can take different forms: abstract form, concrete form. Abstract form is a more general way of representing the problem. So it means that for a set of variables or set of elements, these are the relation that should be valid. But concrete ones are numerical values inside the constraint. So every Pyomo code can have different elements. For example, the sets, variable, parameters, constraints, and objective. So the set can take different values, for example, and also solving that and visualizing that. Okay, and this part that I have specified construct the Pyomo elements. Okay, and then we can visualize that. So let me give you some examples regarding the sets. For example, the set can be defined as the range set starting from 1 to model.n, or it can be defined as an empty set like this, and then using some data file, you can feed the required data into the set. Or the next one is the variables. For example, the way you define your variables is this. Some variables are defined over the sets, some of them are not defined over the sets. They might have some bounds. It means that the variable is changing between these two limits, the minimum value and maximum value. You can initialize them, and they have some domain. It means that what is the type of the variable you are dealing with. It can be real, it can be binary, or if it's real, it can be positive real, percent fraction, it can be something real between 0 and 1, negative real, unit interval, the same as 0 to 1, or non-negative reals, or it can be binary, boolean, positive integer, non-positive integer, negative integer, and non-negative integer. Okay, these are the different types of the variables that you can have in a Pyomo code. Or the parameter, these are the constant numbers that are before solving the problem, we know their values. Okay. Or the constraint. The constraints are very important. These are the equations describing the relation between the variables, sets, and also the parameters. For example, you have to define, you need to choose a name for each constraint. So model.0 is equal to constraint. That constraint, that specific one, is defined over model I, which is a set, and a rule. So you have to separately define the rule. That specific rule is named 0 rule. So that 0 rule is defined over I, the same as here. So if you have I, you have to have I here, and returns the summation of the model.u ij for j in model j less than equal to 1. So that does the summation over j, and the remaining set is I, which is here. Okay, and finally the objective function. The objective function has the same kind of role as the constraint, but in this way we want to optimize it in two senses. It can be minimized, it can be maximized. Okay, and so for the solve statement, this is very important. as I already explained, the solve statement is asking Pyomo to solve the model. So if it's a concrete model, you have to choose a solver and ask the Pyomo to solve the model. But if it's an abstract model, after choosing the right solver, you have to create an instance. It means that snapshot of the model with that given the input data. So you can define a dat file and put those input parameters inside that file, and then ask the Pyomo to solve it for you using the chosen solver. Okay, and here you know that after that, it's the final version. The final step is the visualization. Okay, it's very important to somehow communicate the results of your decision making process for the audience. Thank you very much. In this optimization problem, we are going to solve the problem of biggest rectangle inside a circle. So we do have a rectangle with radius r, and we want to find out what is the maximum area of a rectangle inside that circle. So in order to solve the problem, we have to formulate it mathematically. Now let's talk about how we can do this. Suppose this side of the big rectangle is x, this one is x, this one is y, okay? And then the surface of that rectangle will become 4 times x multiplied by y. And also we do have some other constraints that should be written. The x value is something between -r and r. And also y square plus x square is equal to r square. Okay. Now we want to find out how can we solve this problem. Hello everybody, this lecture is going to be talking about the problem of biggest rectangle inside a circle. Suppose we have the following optimization problem and we want to formulate it as an optimization problem. We want to know what is the maximum area of a rectangle inside a circle. So suppose we do have this graph, we do have a circle with radius r, and we want to know how can we find the maximum area of that rectangle. This side is x, this side is y, and now we want to find out what is the area of the whole rectangle. So it will be obviously 4 times one of these small rectangles. So 4 times x multiplied by y. Obviously you can see on this graph x can move between 0 and r at maximum, and also y is doing the same. It is moving from 0 to r. Then we do have a relation between x and r because they are all on the circle. Then x square plus y square is r square, and the other two constraints are given as follows. X is between 0 and r, y is between 0 and r. Okay, in order to solve it in Python, we need to define some input data and also some decision variables. Now you can imagine what are the decision variables here. So we have 2 decision variables, x and y, and also one objective function, which is called OF here. Then we need to find out how can we write down the equations describing the objective function, how can we define the decision variables, and how should we define the limits of the variables, and how can we finally solve it. So please refer to your Python code, as you can see in the attachment. Then let's solve this all together. Okay, so here you can see that we have formulated the problem here in Pyomo. Let's start with the first tab. The code is written in Jupyter Notebook, and it can be easily run on your machine. It can be a MacBook or a Windows-based kind of machine. So first of all, we import the Pyomo package using this command from pyomo.environ import asterisk. It means import everything. So these are the comments to find out what's going on. Okay, so these are not going to change anything on your formulation, but just give you some hints what's happening. Okay, so for this example, I'm going to use the concrete model. Then using the data that we have for this problem, I'm going to initialize it. Then, for example, R is a parameter because we know the value of it initially, and we initialize it with number 10. You can choose any other number that you want. And then X is a variable, so model.x is equal to var. Bounds are specified here. It's moving between 0 and model.r. Don't write down r because it doesn't recognize r. It only recognizes model.r, which is already defined. And we can initialize it with some value. I have chosen model.r as the initial value. Model.y variable again, and the bounds are the same between 0 and r. And we have initialized that with model.r. Then I do have a constraint C1. Constraint is equal to constraint. Expression is which is describing the model is equal to model x square. I've written the square in this way, and also model.y square is equal to model.r square. And finally, the objective function is equal to expression 4 times model x multiplied by model y, with the sense of maximization, because we want to maximize the objective function. Then on the next tab, let's run the tabs individually. The first tab is run, okay. The second tab is done the same. On the third tab, I'm going to define the solver I'm going to use for solving the problem. Let's have a look at the shape of the optimization problem. It has a multiplication of x by y, and it becomes nonlinear. So I have to use a nonlinear kind of solver. So for this purpose, I have used IP_opt. Solver is specified here. Solver is equal to solver factory IP_opt, and the results is equal to solver.solve name of the model, and I have chosen the model. Okay, you could use any other kind of naming. And then let's run this tab. So this tab is already run, and then the simulation is finished, and I do have the values for the x and y. So if I run it again, you can see the values of x and y equal to each other, equal to 7.071, and the amount of objective function is 200. And also I can get some other results from the simulation. If I run this, I can get some other results. I can fix one of the variables. For example, I can fix one of the variables like x equal to something, which is 1 here, which can happen for you. For example, you want to have a fixed variable in your model and you already know the value, so you can fix it and solve the rest of the problem. So with x equal to 1, y becomes something else, and objective function is something else. So by comparing these two simulations, you can see by manipulating the decision variables, you are getting them far away from the optimal value they can get. So the optimal value for x and y are equal to each other, equal to 7.071. But if you change that and fix some of them, the results become something else. Okay, so for in order to unfix the decision variable and fix something else, you can use this command model.x dot unfix. It means that the variable x is no longer a fixed value, and you can fix something else, or you can't. You can do nothing. Okay, and then solve it again, and you can see the results here. This time y is equal to 1 and x is something else. Okay, and the objective function is found. You can unfix everything, okay, and then solve the problem again and see the results. Okay, so here you can see that there are some useful information regarding the model you have solved: the number of constraints, the number of variables, the objective function, the bounds for everything is found, and also it tells you that the solver has been successful in finding the optimal solution or not. Okay, so you can expand this model to any other application if you want, and that's it for this session. In this example, we are going to solve the following optimization problem. So we want to find out what is the biggest cylinder inside the sphere. So in order to solve that, we need to find out what does it mean by the biggest cylinder. We mean the volume of that cylinder. So in order to calculate that volume, we can easily draw a figure like this. So this h is actually half of the total height of that cylinder, okay, and the volume of that half is equal to h multiplied by the area of this circle. So the area of that circle is pi r square, and multiplied by h will give you the volume of this side of the black cylinder, and you multiply by 2 gives you the whole volume of the cylinder. So the objective function will be equal to OF is equal to 2 pi r square multiplied by h, and the decision variables are r and h. So there are some constraints in this example. So if you look at this graph, you can easily see that the r, small r square plus h r square is equal to r capital square. So r capital is the radius of the big sphere, and r small is the radius of the base of that cylinder. So we do have that constraint, and also we know that the small r is between 0 and r capital. So you see here, and h is as well the same. H is between 0 and big R. So in order to solve that, we need to use the Pyomo package. So here you see, from Pyomo environment, we import everything, and also we may be using the NumPy, and these are the comments which is not going to be used. So we define a concrete model. It can also define as an abstract model, no worries about it. So R is the parameter, we initialize it with number 1, and also H and R are both variables, and they are ranging between 0 and model.r. So instead of defining a new constraint, I just put the boundary of the variable inside the variable definition, and we can initialize it with some numbers between 0 and r, and I use the r here. So, and also we do need a constraint. For example, C model.c is the constraint that is describing the problem for me. Expression is equal to model r square plus model h square is equal to model.r capital square. So as you already noticed, Pyomo distinguishes between the r capital and small r. Yeah, and also the objective function is the following expression here. I'll write it down. So it will be 2 pi r square multiplied by h, and the sense of the optimization is maximize. And since the overall model is a nonlinear programming, I can use the IPOpt solver, and the result is given here. So let's run each tab separately. I run the first tab and then the second tab, and you see the number increases after running that. And then I use this tab. So after passing this tab, the optimization is solved and everything is stored here in my model, and we can print the output. So the R value is 0.82, H is equal to 0.58, and the objective function is 2.42. And I have used 2 points for rounding purpose. And also, if you don't want to use the round function, you can easily print the whole number here. Okay, so you can easily update any numbers that you see in this example and adapt it to your own values. Thank you very much. This example is talking about the fastest route. So suppose we want to go from point A to point B, and this is a lake, half a circle kind of shaped lake. So in order to travel from A to B, we have two options. We can go by boat from the water path. We call it L1 with the speed of V1, or we can walk on the land under the route from L2. We call it L2 with the velocity of V2. Okay, so we want to minimize the traveling time, and we know that the speed of walking and the speed of the boat are different with each other. So the decision variable is the theta. So we want to find out what is the optimal value of theta in order to minimize the total traveling time. So the total traveling time is the time on the boat and the time on walk. So here you can see the objective function is defined as the summation of L1 divided by V1 time 1, L2 plus divided by V2 gives you the time 2. Okay, and also we know that the L1 is 2r cosine of theta. So based on this graph, you can easily see that L1 has such a relation between radius of the circle, which is a known quantity for us, and the cosine of theta, which is the decision variable. And L2 is equal to 2r theta. And we already know that the theta is expressed in radian. So this is the Python code for solving the problem. Okay, so here you can see that first of all, we have to import the Python Pyomo package. So here you see from pyomo.environment import asterisk everything, and also if we need some functions, we might need numpy. Okay, and this is a description of the problem. So we define a model, we create a model called a model is equal to concrete model, and a small r is the parameter we defined for the model. Model V1 and V2 are also parameters, and also we can initialize them based on the input of the problem. Here we assume that V1 is bigger than V2, and we call it 4 and 3. And theta is the decision variable, and it is changing between some bounds between 0 and half pi, and we can initialize it with pi divided by 3. Okay, and also the objective function is the summation of the time we need for traveling between 2 points. So the expression is 2r cosine of theta divided by model V1 plus 2 times model theta multiplied by r divided by V2. And the sense of the optimization is the minimization. So let's run the first two tabs. So I have run the two tabs, and then I specify the IP opt as the nonlinear solver for us, and the model is solved, and it can give us the required decision variables. So it means that theta is 0. What does it mean? It means that we if we go back to the optimization problem description, it means that we should take the water route in order to travel from A to B. That's the shortest path, and we will travel only 2r. Okay, And that's it for this example. Thank you very much. Hello everyone. This example is called Heron problem. So we want to find out if we are given 2 points like A and B on the same side of a line called L, and we want to find out a point D, the green one on this graph, in a way that the sum of the distances from A to D and also D to B are minimum. Okay, the summation of D1 plus D2 are minimum. What are the given parameters of the problem? The parameters, the input data of the problem are L, H1, and H2. Okay, so both of these two quantities are known, and the decision variables are X, D1, and D2. Actually, if we know the X, we know everything else. Okay, so the only decision variable is X in this problem. Okay, so let's write down the mathematical formulation. Minimization of D1 plus D2 subject to some constraints. So on the first triangle, you can see here there is a relation between X and H1 and D1. X squared plus H1 squared is D1 squared. And also on this triangle, L minus X, which is here, square plus H2 square is equal to D2 square. Okay, so let's write it down in Python. First of all, like the other examples, we have to import the Pyomo environment and then import NumPy if we need it. And also we have to define a model. Here it's a concrete model, and also the parameters of the model. There are 3 parameters in this specific example: L, H1, and H2, and we have to initialize them. We have to tell Python that what are the values for them, and also 3 variables: D1, D2, and X. Also D1 and D2 can be found using X, but since we don't know their quantity and the value, we have to define them as variable. And also we know that the range that D1 and D2 can change is between 0 and L. Okay, and we can initialize them as well. And also X variable is between 0 and L as well, and we initialize them as all of them equal to 0. You can choose any other number. And also we have 2 constraints, C1 and C2. The constraint C1 is telling us expression equal model D1 square is equal to model H1 square plus model X square. And the second constraint is telling us D2 square is equal to model H2 square plus model L minus X square. Okay, and the objective function is the summation of D1 plus D2, and the sense of optimization is minimize. Like every other optimization example, we have to run all the tabs one by one and then choose the solver, which is obviously the problem is a nonlinear programming because of the constraints. Okay, the constraints, you can see the nonlinearity terms. Okay, I run this one, so I have specified so far the solver for solving the problem, and the results will contain the decision variables all, and also the objective function. So if I print the results, you can see here that the D1 is 3.89, D2 is 7.77, and X is 3.33, and F1 is 11.66. Okay, and this is a non-linear kind of programming. Thank you very much. Problem. So suppose you have a given a plane triangle, and you want to find out a point like X and Y in a way that the sum of its distances to the vertices of the triangle is minimum. So we are assuming that the coordinates of the triangle are already known. So the location of A, B, C points are known, and what we want to find is X and Y. So we want to minimize D1, for example. Let's say D1, D2, and D3 sum together, and also in order to find the value of each distance, the following formula can be used. Di square is equal to xi minus x square plus yi minus y square. So xi and yi are the coordinates of the triangle. Okay, so in order to solve this problem, we have to know which parameters are known. Xi, yi are known, and the decision variable are x and y. So let's formulate it in Pyomo. First of all, we need to let's say import some libraries. Okay, for example, the Pyomo library, Matplotlib, NumPy, and the random package. Okay, and then we have to create a model. For example, let's say model, concrete model. And let's assume that if we have a triangle like this, the first vertex of the triangle is located on the origin, 0 and 0. Another one is called A and the other one is called B. Okay, so we want to first of all specify the A and B, and then there are two variables called X and Y. These are the coordinates of that central point, and F1 is the objective. So you can see here the model.f1 is objective, and the description is as follows. Okay, so we can do the summation one by one. So this one is the D1 sqrt of model X minus 0 square plus model Y minus 0 square sqrt between X and 0b. So it's here, 0 and B, sorry, it's here. X is 0, Y is B, yeah. And also the last one, this is the point A. So the distance between that point and point A is calculated here, and the sense of the optimization is the minimization. Okay, so like every other optimization problem, we do have to specify the solver, which is IPOpt here for obvious reason, because it's nonlinear programming. Then we have to ask Pyomo to solve the problem for us, and the results are saved here. Let me run the problem here. So this one is run successfully, this tab is run next, and this one also is done. And also if I run this, you can see the values of X and Y are found, the optimal values are found, and objective function is also calculated. Okay, if we want to show it visually, then you can easily see that how they are scattered here. Okay, so this is the point we are looking for it. Okay, thank you very much, and this is the example regarding the Steiner problem. Thank you very much. This example, we want to solve a set of general kind of linear programming approach. So suppose we have an objective function which is the summation of some x, let's say sum over I of ci multiplied by xi, subject to summation of ami multiplied by xi greater than or equal to bm, and we have m constraints and I decision variables. Okay, so bm, I, ami, and ci are known parameters to the model. So in order to solve that, I want to give you an example, a simple one actually, with two decision variables like x1 and x2, and also the coefficients of x are specified here as c, 7 and 12. These are the c1 and c2, ci here, and also A is a matrix specified here, and here we are writing down each row of this multiplication. So 3x1 plus 4x2 greater than 4. This is one row of it, and the other row will be 2x1, 5x2, and bigger than 2. Okay, so since we want to write it down as a general model, and if we increase the number of decision variables or the number of constraints, that should be also working. So we decided to do it in a abstract kind of modeling. Okay, so in order to do that, after we define the model as an abstract model, we need to specify the input data. So in order to do that, we have to create another file with the dat extension, and then specify the sets and also the parameters of the model and so on. Okay, so here you can see that C, since it's defined over 1 and 2, you can see here 1 and 2, the value is 7 and 12, and also the other parameter like B is defined over set M, M1 and 2. You see here that 1 and 2 is here and 4 and 2 is here. Okay, and also finally A is described here. Okay, so let's have a look at the code together. So it's here, let me show you. Okay, so first of all, I imported the required packages. Okay, since we don't need any kind of plotting, I removed the matplotlib importing, and also I don't think I need the numpy, so let's leave it right there. That's fine. If we need it, we can use it. Okay, so we have two imports, and then I have defined the abstract model, set n and set m. Set n is telling us how many decision variables do we have, how many x do we have. Okay, and set m is telling us how many constraints do we have. C, A, B are the coefficients of the model. Okay, C is defined over set n, A is defined over m and n, and B is defined over m. And decision variable is defined over set n. Okay, and we are assuming that these are non-negative reals, positive ones. Okay, and we have some constraints that needs to be created. In order to do that, we need to define model con, or I just named it con. You could name it something else, that's fine. Constraint. This constraint is defined over model m. It means for every constraints we have some rules. Okay, so how should we define that? This is the way we define it. Define con rule, model and m, and return summation of this expression, model a, m and I, multiplied by xi for every I in model n bigger than equal to model b m. Okay, so we are exactly repeating what we saw here. Okay, so let's have a look at this code again. You see, this is the constraint that we have written here. Okay, so let's continue. The objective function is the summation of ci multiplied by xi for every I in sets model n, and the objective function follows this specific rule that we have already defined, so that will follow the rule, and the sense is the minimization. So if we look at the model structure, we see that it's a linear programming one. Then we have to define the solver we are going to use. Okay, and so let's say opt is equal to solver factory glpk. glpk is a solver that can be used for linear programming, and in order to solve an abstract model, we have to create an instance. Instance will be created using this command. It is equal to model.create instance, using the data file that we have in the same root, and then we will ask Pyomo to solve the model for us. Result will be equal to opt.solve instance. So the model will be created and the data will be fed into the model, and this line will solve the model for us. Let me solve the model and see what is going on. Okay, so after the solve is finished, the results are already in the results. For every I in the instance.n, we will print the value of x. Okay, so how should we define the value of x? we have to print the value of instance.xi, but we have to create a loop to tell Pyomo to print every x that exists in the model. And finally, of is equal to value of instance.of. Okay, so in order to have access to the solved values, we have to use the command value instance dot something that we want to see the value. Okay, so let's run this one as well. So you can see that the x1 is equal to 1.33, x2 is equal to 0, and of is equal to 1.33. Okay, so this is a very general kind of model for solving the optimization problem. So you can see here, if we want to increase the number of decision variables, that can be easily done. If we increase the number of decision variables, then we have to change the number of n. Not only is 1 and 2, then we can have 3, 4, 5, and so on. And that model is a general format for solving any linear programming. Thank you very much. This example is called hostile brothers in rectangle. Suppose we have n brothers and we want to find the location of them in a rectangle in a way that the minimum distance between each pair of brothers is maximum. Okay, so the input parameters of this model is the dimension of the rectangle. For simplicity, we can assume that it has a square shape. So then we need to find out the location of each brother. So xi and yi of each brother should be found. And so in order to calculate the distance between each pair of brothers, for every I and j, we have to calculate this expression. Xi minus xj square plus yi minus yj square should be bigger than r square. And also the x should be within 0 and 1, which is the dimension of that rectangle. And y is between 0 and 1. Okay, so y is moving from here to here and x is moving from here to here. Okay, so in order to find out what is the optimal decision for this problem, we need to have a look at the Python code. So first of all, as usual, we have to import the required libraries as we did it here. We have defined it as an abstract model. I have defined the number of brothers as a parameter and made it mutable because we can be able to change it and update it. And also we are trying to find out, we define a set of I with the exact number of brothers. So range sets 1 and model n. J is the alias of the previous set I. L is the dimension of the board. Okay, and I define this function later. Okay, so there are 3 variables in this model: x, y, and r. So x is defined over I, y is defined over I. The bounds of both are between 0 and model L, and they are defined within non-negative reals, and we initialize them using this function initval. So a uniform number between 0 and 1 will be assigned to each variable, and then we have to calculate the distance between each pair of variables. Okay, so in order to do that, we have to create a constraint like C. Model.c is a constraint. It is defined over model I and model j, following the rule C1 rule. The C1 rule is defined for different situations. If we already know that the distance should be defined for different brothers, not themselves. Okay, so it means that if I and j is not equal to each other, then it means that the distance will be calculated at using model.xi model minus model x model.xj square plus model.yi minus model.yj square bigger than model.r square. Okay, that r is the minimum distance between them, and if they are equal to each other, then we have to skip the constraint. Okay, and the next line is describing the objective function, which is the given by expression equal to model r. We are telling Pyomo that the objective function is model r. The sense of optimization is maximization. We want to maximize the minimum distance between each pair, and we choose the solver as the IP-opt. Since it's nonlinear programming, we follow the IP-opt, and then we specify the model.n. We could put this data in a dat file and call that file, and the next step is creating the instance. Model.create instance will feed the data into the model and create the constraints and everything. Then we can ask Pyomo to solve the model, solve that specific instance for us, which will be done. Let me run the code for you. Okay, so first tab, second tab, third tab, and this one. This one will graphically show you what's happening. Okay, so if you want to test it for another set of number, for example, let's say 25 brothers, I rerun this section and the model will be run for a bigger number of brothers. Okay, you can still increase that number, let's say 40 brothers. So to see what's going on, so it takes more time, and then it's for 40 brothers. Okay, thank you very much for paying attention to this example. Okay, this is the hostile brother in a circle. We want to find out the locations of n brothers in a circle in a way that the minimum distance between each pair of brothers is maximum. Okay, so we want to first calculate the distance between each pair of brothers. So here is the formula for calculations: xi minus xj square plus yi minus yj square bigger than r square. So that small r is giving us the minimum distance between each pair of brothers. The next constraint is in order to make sure that all of them are inside a circle with the radius capital R with the center of R and R. So the center is R and R here, and we are assuming that the R is 1, or we can even change that. Okay, so let's have a look at the code for this purpose. Here you can see the Python code. As always, we have to import the required packages. We do it here in this tab. We run it, so it's successfully run. Then we have to define the sets and the number of brothers. So n is representing the number of brothers. I is a range set between 1 and a model n, and j is the alias of I. R is the radius of the circle. Okay, and then we have to give the definition of the variable x and y and r. So x is moving between 0 and 2r, y is moving between 0 and 2r, small r is a positive number. Okay, also there are some rules for calculation of the distance between each pair of brothers. So you can see here, for every I not equal to j, the formula is as follows, and if I and j are equal, we have to skip the constraint. So model has one constraint that is defined over I and j, and the rule is C1 rule. The other constraint that is making sure that all of them are inside the circle, that specific circle, is this one. Okay, so that's obvious that the second constraint should be defined over I for every brother, and the objective function is given by model R, and the sense is the maximization. So we adopt the solver IP-up for this purpose. We give the required parameters to the model. R and N are specified here. We could put them in a dat file and then call that file, and then create the model and create the instance, and ask the Pyomo to solve that specific instance. Okay, so and finally show the results. I will run the code from the beginning to make sure everything is running smoothly. So we have 20 brothers with and a circle with the radius 1. So you can see here that there are 20 nodes here scattered in this circle, and it is trying to maximize the minimum distance between each pair of brothers, and that minimum distance is 0.485. Okay, thank you very much. This is another version of hostile brothers, but this time in a triangle. So suppose we have a triangle with the known dimensions. A and B are the dimensions of that triangle, and we want to make sure that all brothers or hostile brothers are located inside that triangle in a way that their minimum distance is maximized. So first of all, the formula for calculating the distance between each pair of brothers is the same, but now we need to make sure that the red dots are inside the triangle. Okay, so for this purpose I have to make sure that x is always between 0 and b, and y is between 0 and a and b are the input parameters, and also all the dots are below that specific line connecting A to B. Okay, this is the formula for that. Okay, so let's have a look at the Python code. Okay, so here you can see that the Python code is trying to do what? So at the beginning, the first tab is importing the required packages, and then we have to define A, B sets, and N, and also I and J, and also the variables. So this part of the code is similar to the previous ones. So here you can see that we have to define 3 variables, X, Y, and R, and also some rules for calculating the minimum distance. It is a famous rule that we already used in the previous 2 hostile brother variants. And also C2 is the line specifying that we should always be below that line. Okay, and finally that's the objective function. So I run this part of the code as well. Okay, it is run successfully, and I specify A and B and the number of brothers here. Okay, so it takes a bit time to run the code because it's non-linear, and it's has 50 brothers. Okay, and also at the final stage, you can see here that how the brothers are allocated inside that triangle. If I change the number of brothers, let's say there are 10 now, so it will run more quickly. And if I run the code, you can see that how they are scattered inside that triangle. Okay, so you can change it as you wish for your own purpose. Thank you very much. This is the n queens problem. Suppose we have a n by n chessboard, and we want to put some queens on these chessboard without attacking each other, and we want to maximize the number of queens that we put on this chessboard. Okay, so suppose we want to start this problem, and for solving that, we need to use some binary variables. So uij will tell us if a queen exists on the cell I and j. I is representing rows and j is representing column. Okay, and we want to maximize this summation. Okay, so some rules. On each column, for every given column, for every j, we can't have more than one queen on the board. So this is written as follows. So the summation over I over the rows should be less than 1. And also the same kind of similar constraint is here for every given row. The summation over j or over the columns should give us less than 1 queen on each row. Okay, this is another rule, chess rule. And the other rule is the diagonal rules. So it means that on every diagonal or anti-diagonal, we can't have more than one queen. On some diagonals, we can have no queen as well. Okay, so we want to solve this optimization problem in a way that these 4 constraints are satisfied. So there is an objective function, and for every j, and this constraint should satisfy. Every I, this constraint should satisfy. For every I and j, if they are diagonal or off diagonal, these constraints should be satisfied. Okay, so let's have a look at the Python code developed for this purpose. Just a second. Okay, so this is the Python code. Okay, so first of all, I have to import the required packages like Pyomo and Matplotlib, because at the end I want to plot the results. And also I have to specify what is the dimension of the board. So I specify this like that. And I have defined it mutable because maybe I need to change the size of the board. And also I is representing the set of rows, and j is the set of columns. But since they have the same number of the cells, then I have defined them as alias. And model.u is a variable, is a binary variable representing if queen exists in that cell or not, and I have initialized that with 1. Okay, and we have 2 rules, one for row, one for column. So the summation of model.u ij for every j in model j should be less than equal to 1, and this row is defined over every I. Okay, for a given I, that summation should be valid. And the same a similar concept is for every column. So for every column j, summation over I should be less than 1. Okay, these 2 rules. And the other 2 rules are representing the diagonal and anti-diagonal set of rules. Okay, so model.cdiag1 is here, and it is represented over I and j, but not for every I and j. Those I and j that satisfy this specific relation. Okay, and this specific relation is representing the other diagonal of the board. Okay, and the objective function is defined as the summation of the uij for every I and j in the model, and the sense is the maximization. Okay, I run this cell, and then I specify the value of n. How many cells do we have on our chessboard? On each side of chessboard we can have bigger chessboards, and then try to solve it. I solve this problem and show you the results. So you can see here that these are the locations of the queens on the board. So here we have only 1 queen on this row, 1 queen on this column, 1 queen on this row, and 1 queen on this column. And the final tab will save that figure as a PNG file in your directory. Okay, so I can test it for a bigger kind of chessboard, let's say 16. Okay, and if I plot it, you can see here that this is the new kind of allocation of the queens. Thank you very much. So this problem refers to circle placement in a rectangle. So as you can see in this example, we do have some information regarding the a number of circles. Let's assume that we do have n circles, and what we know about the problem is that the radius of each circle is known. As you can see, we can represent them by Ri, but the question is, how can we place them on a plane surface, on a rectangle shaped surface, without overlapping each other, and the surface of that specific rectangle is a minimum value. So in order to formulate that, we have to create some constraints and an objective function. The objective function is multiplication of L multiplied by W, which is length and width of that rectangle, and for each pair of circles we do need some constraints. For example, the distance between the center of these two circles should be bigger than Ri plus Rj square in order to avoid overlapping, and also for each x and y, which are representing the center of each circle, we should have the following two constraints. Okay, so these are actually, each constraint is two constraints actually. So Ri is between xi is bigger than Ri and is lower than W minus Ri, and yi is bigger than Ri, less than L minus Ri. Why? Because we don't want the circle to get out of this rectangle. Okay, so in order to show you what's going on, first of all, we have to know the input data for this problem. It means that for every I and j, for every I, we have to know the radius of each circle. So in this way we can work on it. Okay, so let me show you the so as you can see here, we do have 6 circles, and for solving the problem we have to find the optimal locations of them. So here you can see the Python code required for solving that problem, and as usual we have to import the required packages, for example Pyomo, Matplotlib, NumPy. We don't need the random package, so I remove that. And also we have to create an abstract model, so we can then easily change the number of circles that if we want. So model I is a set, model.j is another set which is in alias with the previous set. R is a parameter which is defined over set I, and also we do need some constraints, okay, and some decision variables. The decision variables are the centers coordinations x and y, which are bounded with Ri and a big number, because as you saw in the formulation, each x is between, for example, L minus Ri, but we don't know the value of L. So for simplicity, I have chosen a big number here. The same philosophy holds for y and also for W and L. So W and L are positive numbers between 0 and 100, for example. I have initialized all of them. And also for every I not equal to j, we have some constraints. For example, here you can see that model.xi minus model xj square plus model y.yi minus model.yj square should be bigger than an expression like this, Ri plus Rj. square. But you might ask me, why didn't you say I not equal to j, and you said I greater than j? This is because if we calculate the distance between two circles, and let's say 1 and 2, then we don't need to calculate the distance between 2 and 1. We just need to calculate it once. Then for the rest of them, we should skip the constraint, and model.equation 1 is following that specific rule. Okay, so rule 2 is telling us x should be less than w minus r. This is another constraint, and the other constraint is for y's. So model.yi is less than equal to model L minus ri. And the objective function is the multiplication of model.w multiplied by model.l. And the objective function should be defined here. Model.obj is equal to objective rule is objective rule here, and the sense is the minimization. The solver chosen for solving this problem should be capable of solving nonlinear programming. Then the instance will be created using the dat file associated with this example, and then we will ask Pyomo to solve it for us. Okay, so let me run each tab one by one. Okay, and this one, number 3, and the final one. Okay, so as you can see here, the optimal locations of each circle is specified and plotted. So let me give you a very quick introduction how I have plotted this graph. So first of all, we have created a fig is equal to plot dot figure fig size. So you specify the size of your figure here, and theta is a linear space between 0 and 2 pi, which is divided into 100 points. And also I have used the scatter command for putting those dots. So for each value of x and y, as we have a for loop here, we put dots here on the surface, and the x center values are also calculated. The center of each plot is here. The scatter is plotting the circle, and the x, c, and y, c, which is representing center values, are created here. And then you can see the graph here. So the solution is graphically shown on these plots. I can also specify the labels for x axis and y axis. Thank you very much. This is the problem of circle placement in a circle. So we do have n circles with known radius, and we want to put them inside a bigger circle with the minimum surface possible without overlapping each other. So we have to write down some mathematical equations that represents the condition described. So first of all, for each pair of I and j, we have to write down the distance between the centers of them, xi minus xj square plus yi minus yj square, bigger than ri plus rj square. So ri and rj here are the radius of the both circles. And also we want to make sure that each small circle is completely inside the bigger circle. So xi minus r, which is the center of the bigger circle, plus yi minus r square less than r minus ri square. Okay, so in this way we are making sure that all the circles are inside the bigger one without overlapping each other. So let's have a look at the Python code and see how it works. First of all, we have to import the required packages. Pyomo.environment import asterisk everything, import matplotlib.pyplot as plt, and import numpy as np. Then let me run this tab, and then we have to define the optimization model. We name it model. Model is an abstract model, and model I is a set representing all the circles, and also set J is the alias of set I. We have parameter R, which is now here is the parameter, known parameter, and also we do have three variables, x and y and radius. Radius is the radius of the bigger circle. Okay, so the dimensions and the bounds of variables are defined here, just some big numbers to avoid plus minus infinity. And also we do need some equations representing the distance of each pair of circles. So I less than j returns this expression. So as I already explained, we just do not only say I'm not equal to j, because this way it will calculate I and j and I. So in this way we are avoiding unnecessary conditions. Else return constraint skip. So this means that, for example, if I and j are equal to each other, it's not needed to be considered in this constraint. Model.eq1 is defined over I and j. The rule that should be followed is rule eq1. And model eq2 is a constraint defined over I to make sure the circle is inside the bigger one. Rule eq2 is model x minus radius square plus model y minus model radius square, less than equal to model radius minus model dots ri square. And also we need an objective function which is the model radius here. So we can say that instead of calculating the surface of that circle, we can say, okay, minimize the radius of the bigger circle. These should give you the same kind of results, and the sense is the minimization. Okay, we need to read the input data. So here let me show you the required data. Just a second. Okay, so this is the required data for this problem. As you can see here that the parameters are running from 1 to 6, and the radius of each circle is already specified. Okay, so the model will read this stat file and feed it into the model. The results are obtained. Okay, let me run this tab, and also this one. The model is solved, and we can graphically see what's happening here. So you can see that the minimum radius of the bigger circle is this quantity. Okay, you can test it for the objective function pi r radius square, so to see it will give you the same results. Okay, the value of objective function is different obviously, but the decision variables will remain the same. Thank you very much. Circles with known radius inside a half circle without overlapping each other. So the first constraint that should be satisfied is that any pair of two circles should not have any overlap with each other. So this the distance between their centers should be bigger than ri plus rj square, and ri and rj are the known parameters of the model, the radius of those small circles. And also they should not be out of the circle. Okay, and finally yi should be bigger than ri. Okay, so in order to see how can we code it in Python. I will show you quickly how we can do it. Okay, so first of all, as before, we have to import the required packages: Pyomo, Matplotlib, and NumPy, and then we define the abstract. So here you can see that we have a set I, we have a set j, which is the alias of set I, parameter r. We have to give the model the radius of each small circle, and also we have some variables, decision variables are x, y, and radius. So x can be between 0 and, for example, a big number. 15 is a big number for this purpose, and initialize it with some number. And also y can be initialized as 4, but the bound for yi is between ri and 15. Okay, so and the radius is a bigger bound has been chosen for radius. And also we can say, okay, if I is less than j, then this constraint should be satisfied. So and then we can everything is defined here. So there is another constraint telling us that all the circles should be inside the big circle, and the solver is chosen as the IP op since it's nonlinear, and also the data of the model, which contains the radius of each circle, is also specified. So you can see the data file here. Okay, and once we you can change the radius of each circle, that should be fine. And also finally you can plot the results at the end. So I run the model, the whole model, and check the results for you. Okay, so you can see here that the results are obtained here. I can rerun that, see if it gives any other response. Okay, so it is solving, and the minimum radius is this number. If I give any other kind of initial solution for that, so let's change the initial solution. Let's say x is 3 and y is, let's say, 5, and rerun the whole model again and check the results. Okay, you can see that it gives you another answer. Okay, so since the problem is nonlinear, then it is expected to be sensitive to the initial value you assign to your variables. Okay, so by changing the initial value, you can see the objective function is changed. Thank you very much. These examples, we already know the radius of all circles, okay, and we do have n circles, and we want to place them inside the triangle at minimum surface without overlapping each other. So we have to write down some constraints to describe the problem. So as you can easily see, the area of the triangle is calculated by xh multiplied by y up here, multiplied by half. It gives you the surface of the area of the triangle. Okay, and the first constraint can be easily understood because it is telling us that each pair of circles should not have any overlap with each other. And also we can see some other constraints here. I will explain them to you. So first of all, we have to write down the equation that describes this red line. So this red line is passing through the origin and also this specific point, x up and y up, and this line is described by this equation. And also we have another line, the blue one. That blue line is passing through this point, xh 0 and x up and y up. So the relation between these parameters are given here. So this is the equation describing the blue line. And also we know that we need to satisfy some constraints. So the center of these circles should be, for example, on the right hand side of the red line and the left hand side of the blue one. This is one constraint. And the other one is that the distance between the center to the red one should be bigger than the radius of the circle. And also the center to the blue one should be bigger than the radius of the circle. Okay, so these two constraints are given here. So these two are telling us, for example, we are below the red line and on the left hand side of the blue one. Okay, and also these two will specify that the distance between the center of the circle and the line is more than the radius of that specific circle. Okay, so we have to write down the Python code to solve this optimization problem, and the decision variables are the location of the centers, and also the radius of them are already known for us. Okay, so let's talk about the Python code. So first of all, we have to import everything that we need, then define the sets I and j. We already know the meaning of them because I is representing each circle, j is the alias of that, r is a parameter and which is specified by us. It is telling us how much is the radius of each circle, and also we have to define some bounds for the variable x and y. So it's between r and a big number, and y up and xh and x up are already unknown, and the area is already the objective function for us. Okay, so we can tell that, okay, if I is less than j, then it means that by just writing down this inequality, we can make sure that any two circles are not overlapping each other, and then we are making sure that we are below the red line, we are on the left hand side of the blue one in this one, and as you can see, these two equations are defined over I. And also the distance between each center to the red or blue lines are more than the radius of each circle. Okay, and also this is another one that we already talked about it. Also we should say that, okay, so x up is less than xh. Okay, this is an assumption, and also the area is specified here. Okay, so these are the constraint and the objective function, and also the input of the problem is described here. So the radius of the circle should be specified in a dat file. Okay, so I run the problem for you and see the results. Okay, so the problem is run, and you can see here that the area of the circle is found, how much is h, how much is w, and so on. Okay, and you can also, by using this command print results.solver.status, and you can find out what's happening to the different variables like x, y, what is the upper value, what is the lower value, what is the exact value of it, and also is it fixed or not fixed, and x up, x h, y up, and the area. You can also have some information regarding the constraints and so on, and each equations. Okay, normally you don't need that kind of information, but if you want to have access to them, you can easily use this command to find out more about what's happening inside your model. Thank you very much. In this example, we do have n equal size circles, and the radius of these circles are unknown. We want to find the biggest value of r that can have. In this example, we are about to allocate n equal sized circle inside the unity circle, and we want to find out the maximum radius of these equally sized circles. And the big circle has the radius equal to 1. Okay, the condition for this specific optimization problem is that no two circles have any overlap with each other, and they are all inside the big circle. So first inequality is telling us they are not having any overlap. The second one is making sure that they are all inside the big circle, and that big circle is the center of that big circle is located on the point 1 and 1. Okay, for simplicity. Let's have a look at the Python code. So first we import every required package, then we define an abstract model. N number of circles is a parameter. It is mutable, so it can be changed. I is a range set starting from 1 to n, which is the number of circles, and j is the alias of I. R, x, and y are variables. They are changing between a small number and 2. And also we need to define some rules for that. As we said, the first rule is making sure that no two circles have any overlap. The second one is making sure they are all inside the big circle. And the objective function is, let's say, r square or r. Okay, so we can maximize r or r square. So let's maximize r. Okay, and also instance will be model.create instance. So after this line, all the constraints will be created and supplied with the input data, and also the results is obtained here, opt.solve instance, and the created instance will be solved using the solver that we already specified. Okay, and finally the results are plotted here. So I run the code for you and show you the results. Okay, so here you can see that for 20 circles we can have these results. Okay, and the location of these small circles and as well as the radius of them is found. Okay, in this example we are going to solve a very fun optimization problem. Suppose you are going to play the game called Clash of Clans. So in this game you have to train your troops to fight against other clans. Okay, and each of your let's say soldiers have different characteristics. They have maximum different maximum hit points, or this example is referring to the Clash of Clans game. We are going to model it as a linear kind of programming. If you are familiar with this game, you do have different troops, and each of them has different characteristics. The amount of hit points it can tolerate, the amount of damage it can cause, and the training time is different for every single troop. And sometimes you want to attack your enemies and you want to have maximum hit points, and you might want to maximize the attacking capabilities, and you want to do it at the minimum training time. Okay, So depending on how much you want to tolerate damage, or how much damage you can cause, or how long does it take to train your troop, or how much cost does it create to train your troop, your strategy for training the troop is different. So as I said, depending on your troop, they have different requirements and different costs. So some of them take more time to train and they use more elixir, okay? And so in order to find out the best strategy to train your troop, you can create an optimization problem and solve it for yourself. So as I said, there are multiple number of troops that you can train, and each of them has its own characteristics. So in order to do that, the attack capabilities of each troop is stored in a parameter called attack, or heat, or time of training, and xi is telling GAMS how many of each troop you are going to choose. So obviously you have to choose the integer kind of variables to model that properly. And also the housing of the camps are limited, so xi multiplied by housing summation should be less than the camp capacity. And also based on the availability of your elixir, your training costs should be limited. Okay, so for solving this model, you do need to have the different characteristics associated with each troop. For example, in this dat file, you can see that different troops here, you can see them here, have different characteristics: housing space, damage they can create, training cost in using red elixir or dark elixir is different, the amount of hit point they can tolerate is different, training time is different for all of them, and the capacity of your camp should be specified here, and the availability of your red or dark elixir is also specified in this Python code. Okay, so let's have a look at the Python code itself. So first of all, as usual, we have to import all the required packages, and then we have to declare the parameters that we are going to use. For example, set I is representing every troop you have, and also these parameters like housing space, damage, training cost red, training cost dark, hit point, training time, camp capacity, and also red elixir availability and dark elixir availability should be specified. And also how many of each troop you have to train should be defined by a variable called x, and that x, for example, since your camp has 280 I think capacity, so the number of troops cannot be more than that, and also they are coming from non-negative integers, so positive integers, and initialize them with 0, and also total attack capability, total hit point, and also the time required for training those troops is also specified. So there are some rules or some constraints that are defined here. I will explain some of them for you. For example, the amount of damage, total attack, is xi multiplied by damage I summation over all I in the model. And also the total housing space should be less than your capacity of your camp. And also the required red elixir should be less than your available red elixir, the same for dark elixir. And also the total hit point is defined over hit point multiplied by xi summation over I. And also finally the training time is defined as follows. So we do have 3 objective functions. This is the tricky point. Okay, so in Pyomo, you can't have more than 1 objective function. Okay, so that's fine if you define 3 objectives It doesn't depend what name you choose here. This is the keyword which is important here. But you can define them, but you can't have them all active in your model. So you specify your solver. I use GLPK because it's linear integer programming, and you have to deactivate 2 of them and just keep 1 of them. So I deactivate objective 2 and 3. I have activated objective 1. It's not really necessary for the first time because it's already activated. And then create instance using the data I already showed you and solve the results. It gives you the final solutions. So it can tell you that if you want to maximize the damage, you have to put all your efforts in training wizards, okay, and 1 goblin. Or, for example, if you want to make the objective number 2 activated, let's have a look. What was the objective 2? Objective 2 is total hit point, okay? So if you want to maximize your hit point, you have to train giants, okay? And that's it. So you can change your objective functions, you can change your availability of red elixir or dark elixir and see what will happen to your capability of the troops. Thank you very much. Okay, in this example, suppose we have a plane and okay, in this example surface. Okay, this example is referring to the problem of finding biggest circle on a surface. Okay, this example is referring to finding the biggest circle on a surface with some obstacle. So suppose we do have a given surface. For simplicity, we have assumed it's like a square and the dimensions are equal to 1, 1, and 1, okay? 1 and 1. And also there are some points are specified here. We want to find out the location and the radius of the biggest circle that can be placed on the top of this surface without this example is referring to the problem of finding biggest circle on a surface with some obstacles. So suppose we do have some obstacles here on the surface, and the dimension of that surface is 1 and 1. It's like a square, and we want to find out the location and the radius of the biggest circle that we can place on the top of this surface without overlapping any of these obstacles. Okay, so first of all, we want to make sure that every obstacle is outside the circle. Okay, so if the center of the circle is specified by capital X and Y, then xi and xj and yj are all already specified for us. These are the coordinates of the obstacles. And also we want to make sure that x is bigger than r, because we don't want to have a circle outside the surface, and also x is less than 1 minus r, so the circle is not coming out of the box from this side. The same philosophy holds for y. Okay, so let's have a look at the Python code for this purpose. Okay, So first of all, I import every required packages, and also I define the abstract model. Parameter n is telling us how many obstacles we have, and also the range of them is specified here. So we might need a random initialization. Okay, so for this purpose I define this function. So define an init val model and I. For every I can provide you an initial kind of location for those obstacles actually, and also the x, y, and r are or variable decision variables. They are positive numbers varying between 0 and 1. Okay, so they are all on this surface. Okay, so we want to find out the area of that circle as the decision variable or the objective one. There are some rules. The first rule is making sure that every obstacle is outside that circle. The other one is telling us that x is bigger than r. I couldn't put r here on the interval because r is a variable, and y is bigger than r as well, and y is less than r, 1 minus r, and x is less than 1 minus r. Okay, as we discussed before. And also the area is obtained by this formula using this constraint. So the objective function is obtained using this expression model.area, and the sense is maximization. I choose the solver. Okay, I choose the solver. I can specify the number of obstacles here. And finally ask matplotlib to show me the obtained solution. I run the code and see the results. Okay, so we have to wait and see the results here. So 50 random obstacles are generated on the graph here, you can see, and then the center of that circle is found. The radius of that circle is also found. You can see it here. Okay, so you can easily change the number of obstacles. Instead of, let's say, 50, let's try 10. Okay, and rerun the code. So for 10 obstacles, the location of the circle is also found. The radius is obviously bigger than before, and also the location of the center of this circle is updated. Thank you very much. Okay, this lecture is referring to calculation of center of mass. For this example, suppose we want to formulate it as an optimization problem, and the input data of the problem is as follows. So we want to find out the center of mass of a given set of objects, which their location and their mass are known, and we want to find out what is the x and y coordinates of the center of mass. Okay, so based on the formula, we know that the x of the center of mass is calculated using this formula: xi multiplied by the mass of object I, do the summation over I, divided by summation of all masses. The same formula is for applies for the y coordinate. Okay, so let's have a look at the Python code for this purpose. Okay, so you can see here that at the beginning, as usual, we have to import all the required packages. Here we do need to import pyomo.environment, import everything, import matplotlib.pyplot as plt, import numpy as np, and import random. Okay, we define an abstract model. n is representing the number of objects. I specify the default value equal to 15, but you can easily change that. In order to be able to change that, you can define it as a mutable parameter, and then you have to define the set of objects. If you need the location and also the masses of the objects can be specified as the input parameters, okay, but you can define them as some random numbers. So you do need to specify them. So X location, Y location are the locations of the objects, and the mass is already specifying the mass of each object, and you initialize these parameters using the defined function. So the interval function will give random coordinates to X and Y, and also the interval M is giving you some random masses to your objects, but you can also specify them in a file or something like that. And also there are two decision variables, X and Y, the center of mass of the overall objects. And since we are trying to find them in a since we already specified the X and Y locations between 0 and 1, then the center of mass will be somewhere between 0 and 1. Okay, so I define them as variable, non-negative ones, and I initialized the X and Y's using this formula. So initialize some constants, okay? And then we do need to write down two constraints, one for X, one for Y. X is calculated using this formula. It's equal to summation of X location multiplied by their mass, do the summation over all the i's in model I, divided by sum of all masses in the system. The same concept holds for Y, and you have to define some constraint for that to be calculated. Then the objective function is the important part here. So actually in this problem we don't have any specific objective function. We just have some constraints that should be satisfied. So you can simply specify X or Y as your objective function, and you specify the sense as maximization or minimization. It doesn't matter, because you want to, and there is only one unique solution for that, and there's nothing to be maximized or optimized. Okay, so then you will have to use some solver. So since it's a linear programming, it's better to use GLPK as the solver. And then initially I have specified the default value of the objects, the number of objects is 15, but you can definitely change that. You can say it's 5 or 7 or anything else, or you can leave it as it is, it's equal to 15. And then ask Pyomo to solve it for you, and finally you can plot the results. So let's run the code one tab by one tab. Okay, this one is run successfully. How about this one? This is also done, and the final one. So you can see here that there are 5 objects randomly generated here. So you can see them here, and if I change the numbers, let's say it's 6. Okay, so I run this model again, I calculate it. So there are 6 objects here. One of them is very small. So it's here. One of them is here, 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 and here, and here. Okay. So for 6 objects, the location of center of mass is found. You can also print their values. So X of center of mass is found using the formula. So it's here actually. So this is the value of the center of mass. You can also print it if you want. And this is it for this example. Thank you very much. Hi again. This lecture is referring to the problem of center of masses, but this time it's referring to negative mass. What does it mean? Suppose you have a plane surface and you do have some holes inside that surface, and you want to find out what is the center of mass of this new shape. Okay, so in order to solve the problem, we can follow the same formulation, which is x is equal to xi mi divided by summation of m, and also the same for y, but with small differences. So we can assume that the center of mass of the plane is located at its center point. So suppose the dimension of the surface is 1 by 1. Suppose it's a square and the dimensions are both equal to each other, 1, and this side is 1 as well. So the center of mass is located at the center of this square, half and half. Okay, and we do have some holes inside that plane. So you can see here on this graph there are 3 holes, and depending on their surface, you can see that they can have different masses. So the mass is proportional to the area of each circle. Okay, so for simplicity, we are assuming that we know the locations of each hole and also the surface of each hole. Then in order to solve that, we can easily apply the same formula. So let's have a look at the Python code. So as I said, the mass of the plane is positive because it exists, and those holes, since they do not exist, we will consider them as negative masses. Okay, so here you can see the Python code. So here, first of all, we import the required packages, and then we define a abstract model, and also there are some parameters needed, the number of circles. Let's assume the default value is 5, and a set I, which is ranging from 1 to n. We do need 2 random generator in order to scatter the points on the plane and also their masses. And then x location, y locations are also are the parameters, input parameters, and mass as well. And the variables, we do have 2 variables, model.x, model.y. These variables change between 0 and 1 because the center of mass will be inside that plane. And the rule is the same, but with a small difference. This time the mass of the plane is, let's assume it's proportional to the area of that. Then we can say that it's 1 multiplied by half minus summation of those m's, and actually the area of them is specified here. The m is the radius of those circles, and divided by the summation of those areas. And we can do the same for y. And as I explained, and since this example doesn't have any specific objective function, you can choose any of your decision variables. It's a linear programming approach. You don't have any nonlinearity. If you see a square here, since m is known, there will no nonlinearity be created. Sorry. And also we have to choose the solver. I chose GLPK, and then I will create the instance, so everything will be fed into the model, and use the matplotlib to draw the graphical shape to show the results for us. So For simplicity, I have chosen 2 points, one for the solved solution, the red one you can see here, and the yellow one is exactly at the center of that square, and those white ones are representing the holes inside that plane. So as far as those random numbers are not overlapping each other, then the solution is correct. Otherwise, this approach doesn't give you a valid solution, okay? Because those white ones should not overlap each other to be able to represent their weight on the solution. I run it again to show you the new results. So every time you run the code, it will give you another set of new solutions. Here you can see that the center of mass doesn't change that much compared to the center of that square. I run it again, hoping I can get a better solution. So this time you can see why this solution is not correct, because there is an overlap between these two white ones. And so this new calculated center of gravity or center of mass is not precise, because those masses are calculated 2 times. I run it again, hoping I can get non-overlapping kind of circles. Okay, so here you actually there is overlap. I run it again. If you manually specify their location, you don't need to run it multiple times. Okay, so here you can see that since all of those white circles are this side of the plane, then the center of mass will move to the opposite direction. Okay, thank you very much. Okay, this example is referring to the problem of minimum queen to cover the whole chessboard. Okay, suppose we have a chessboard with a given size, a special given size. As you know, chessboards are 8 by 8, but suppose a very special case, it is 4 by 4, and we want to know what is the minimum number of queens required to protect all of the cells. Okay, and these queens should not attack each other. So one of the configuration is shown on this graph. So here you can see that there are 3 queens. This is the minimum number of queens required, and all of the rows are protected. For example, this row, this row and this column are protected by this one. This column and this row is protected by this one, and also you can see here that this guy is protecting this column and this row, and also these 2 cells, and this cell and this cell. Okay, so with 3 queens I have covered all the cells. Okay, but how can we solve this in general mode? So if we are given an n by n chessboard, how many queens are required? What is the minimum number of them required? Okay, so we want to minimize the number of them, so I have to define a binary variable called uij, which is telling us at cell I and j if there is a queen or there is not a queen. Okay, so here this is what we are doing. For every given column j, summation over I should be less than equal to 1. It means that not more than 1 queen can exist on each column, not more than 1 queen can exist in each row, and also on each diagonal the number of queens should be less than 1 or less than equal to 1, so it can be 1 or not nobody. And also for every for the anti-diagonal cells, the same condition should happen as well. Okay, so let's continue. The last condition, so whatever we talked about is this problem is called minimum queen to cover the chessboard. So in this specific problem, we are trying to find out what is the minimum number of queen required for protecting or covering all the cells. Suppose this example is going to be solved for a very special case of chessboard with 4x4 dimensions. As we know, usually they have 8x8, but this is a special case. So you can see here, by only 3 queens located at this specific location, all of the cells are protected. For example, this cell is being protected by these 2 queens, and no 2 ones are attacking each other. Then we need to define it as an optimization problem if we want to solve it for general case. So we do the summation over I and j, and uij is a binary variable representing the fact that if a queen exists on the cell I and j, and also for every given column like j, if we do the summation over the rows, then there will be not more than 1 queen on each column, and also there will be not more than 1 queen on each row, on each anti-diagonal, and on each diagonal rows of cells. Okay, and so these 4 conditions are designed for queens not to attack each other. And also we need another one. Okay, so if we just use these 4, then the obvious solution to this problem will be no queen at all. Okay, so we need another kind of constraint saying that for every I and j, if we do the summation over uc and r, then for every diagonal or anti-diagonal, or every row or every column passing through that cell, the summation should be bigger than equal to 1. Okay, so it means that it should be protected by at least 1 queen. Okay, so if we solve that, we can see the results for the 4x4 case. So if n is 4, then the solution is that. And also we can test it for a bigger chessboard, 6x6 or 8x8, the traditional one. So the 8x8 chessboard can be protected by only 5 queens. And if we make it bigger, let's make it 10, then it can be protected by 6 queens. Okay, so I'll show you the Python code for solving this specific optimization problem, which is a linear programming, mixed-engine linear programming. As usual, we import the required packages. N is representing the size and dimension of the chessboard. I is representing the queens, different queens, and j is the alias of I. U is a binary variable defined over I and j. So we need to define some rules for not attacking to each other. So these 3 rules are designed in order to the first one, let's have a look at this one first. So the first one is telling us that each cell I and j should be protected by at least one of these conditions. So there should be a queen on the diagonal or anti-diagonal, or I is equal to R, or J is equal to C, or from the same row, from the same column, or from the diagonal or anti-diagonal. And also the remaining ones are designed in order to the queen do not attack each other, as I explained. And the objective function is the summation over uij for every I in model I and for every j in model j. The solver is chosen to be GLPK because it's linear integer programming. And then we provide the model to the instance creation. The instance will be created and the results are obtained after the solve. And finally, the solutions are graphically shown here. Okay, and finally it can be saved somewhere on your machine as a gmean n queen.png, for example. Okay, so I run the code for you. It is running now. So for simplicity, we have assumed that n is changing between 4, 6, 8, and 10. You can change that number as well. Okay. I hope you learned something useful in this lecture. Thank you very much. This example is referring to the connected trees. So we do have some random points on the surface. Suppose here we have 10 points, and what we want to do is try to find out the graph, which is a tree without any loop, which is a connected one. Okay, so we want to find a connected graph which has no loop inside it. Okay, so in order to solve this problem, we need to find out a way that first of all we need to find a connected graph and then try to avoid having any kind of loop. Okay, so in order to do so, we need to think about how we should do that. First of all, in order to make the graph connected, first of all I put some demand on each point, a virtual demand, so it doesn't exist in reality, but we want to find out a way that how can we supply all of these demands. So in order to do so, I assume that I have a generating unit at one of the points, just one of the points. Let's say point number 1. You can put it everywhere else, and then try to find a way that connect these production point or generation point to the rest of the points. Okay, and if you can formulate that, then it will be solved. Okay, so let's think about what kind of variables do we need in this formulation. Okay, this example is referring to the problem of connected trees. Let me describe the problem for you. First of all, we do have a number of points scattered on a surface. Suppose we do have just 10 points in this example. And in order to solve the problem, we need to think about two different constraints. First of all, the graph should be connected and it is a tree. The definition of the tree is that it's a connected graph without any loop. Okay, so how can we solve that problem? Okay, in order to solve that, I assume that at every node there is a virtual demand that should be supplied. So every node has a demand, no matter what the amount is, but we know that this demand should be supplied. And in just one of those nodes, I put a production plant, and that production plant should be able to supply every demand in the system. So this will give us the condition of connectivity. In order to do so, let me think about what kind of variables do I need. First of all, which node should be connected to each other? So then definitely it will be a binary variable. Let's name it uij, and dij is the distance between node I and j. Okay, and for every node I have to write down the balance of supply and demand. So at every node, gi minus li is equal to the outgoing flows. But keep in mind that only one of the nodes has gi, or generation or production. Okay, just node number 1, or any other nodes that you want. For simplicity, I chose node number 1. And also there's another condition. The flow only can exist on the lines that are connected to each other. For example, let me give you an example. For example, if 1 is connected to 4, then uij is 1. Then flow can get a non-zero value. So the flows are assumed to be positive as well. Okay, so if I solve that, then the connected tree can be found. So let me show you the Python code. So beginning, first of all, as usual, we have to import the required packages like Pyomo, Matplotlib, NumPy, and also the random. And then I create a model, an abstract model. Model n is the number of nodes. For default value, I put 8. But you can change it. I made it mutable. It means that you can update it. Model I is the set representing all the nodes from 1 to n, and also j is the alias of I. Model u is the variable, is a binary one, indicating I is connected to j, I to j. Flow, that's the same, and I define it as a non-negative real. G is the variable representing how much you are producing. I defined as just one variable. It's not needed to be defined over a set because only one of the nodes has production or generation, and the objective function at the end. And so maybe we need to initialize some variables like x location and y location. These are not variables, these are parameters, because we already know where these points are allocated. In order to initialize the parameter d, which is the distance between each pair of nodes, we have to define it as a parameter here. You can see it's over a model I and j. It takes non-negative real numbers, and I initialize it using this rule. This rule is the famous rule, sqrt of x location I minus x location j square plus model y location I minus model y location j square, and this will give the distance between each pair of nodes. It's a parameter as well. And the balance equation, which is written on every I, is defined using this rule. So for the first I, we want to put g only on the first I, and for the rest of them there is no g here. Okay, and here this quantity is the virtual demand at each point, so I just defined it as the I divided by model n. So and that's it. What else is remaining? Rule number C2 is the fact that if u is non-zero, then flow can get a quantity. And also the objective function is multiplication of URC multiplied by DRC for every R in I and C in J. Okay, and also what else is remaining? The objective function is model.of, the sense is minimization, solver is GLPK, and model N, let's assume there are 10 points. I initialize the instance, solve the instance, and print the objective function. And also, first of all, I draw the points, random points, generated points, and also show the solved results. I rerun the program. This one, since the points are randomly generated, each time you plot the graph, you might get a new one, but that should be fine. And the program is running. So you can see here that generation is on point 1, and it is trying to supply every node. So the nodes are like this, but when you solve the problem, the connected tree is here. So why is it always tree? Because if you add any additional line, then an extra cost will be added to the objective function. So the program naturally will avoid that. It is not only connected, but it avoids any loop. Thank you very much. This example is referring to a spanning tree with degree constraint. So as you might have seen in the example of a spanning tree, we defined some virtual demand for each node, and then try to find out how we can create a graph, which is a tree, a connected one, but without any kind of loop. So now we want to find out more characteristics of the graph and enforce some additional constraints. So if you look at this graph, which is a tree, we can easily calculate the degree of each node. For example, the degree of node 6 is 1 because it has only one edge connected to it. Degree of node 1 is 2. It has 2 edges connected to this node. And the degree of node 9 is 3, and so on and so on. Okay, so maybe in some cases we want to limit the degree of each node. So in order to do so, we have to limit the number of edges that can be connected to a graph, to each node. So we can write down for each I, we can write down such equation or constraint: UIC plus UCI should be less than n degree, and the summation should be done over all the C except I. So we add this constraint to the formulation and see the results. So you can see here, if I limit the degree of each node to, for example, 2, then the same connection, the same dots are connected to each other in a different way. So here you can see that the maximum degree is 2. But how should I write it down? Let me show you the Python code. Okay, so here you can see the Python code. Initially I import every required package, and then I define the required variables. So the variables are the same as the example minimum spanning tree, and but we have to add a new parameter called maximum degree. So a max degree is a parameter, it's a mutable parameter. You can specify a default value for it or not. And also the variables are exactly the same. Then I create some random locations for those dots and calculate the distance between each pair of them. Okay. Then there are some constraints for this model, and as we discussed before in the previous example, Each node should follow the balance rule. So how much we have generated is equal to how much we are consuming or exporting. So here only for node 1 we have a production or generation, and at each node we have some amount of demand, let's say I divided by model.n, or you can specify something else or a constant number or whatever you want, and then how much exporting, how much importing from the other nodes to do the summation, and this constraint will create the balance rule. And then the other constraint is telling us that if node is connected to each other, if two nodes are connected to each other, then a flow can exist between those two nodes. And this one is telling us the maximum degree of each node, how should it be specified. Okay, so model UIC plus model UCI, summation over C, but for some specific C's, not all the C's. If I is different with C, because we are not connected to each other, to ourselves, and it should be less than model degree. And the objective function is the same as before, U multiplied by D, summation over all I and C. So here, let me give you a point here. So here you can see that if we write down this the code in this way, what will happen? It will put the R and C for every possible combination of R and C, R in I and C in J. Okay. This way will also create some additional U when the R and C are also each equal to each other. So to avoid that situation, I add an extra kind of specification here. So here, if R and C are exactly equal to each other, then so if R and C are not equal to each other, then this summation should take place. Otherwise, it will create some situation that R and R, for example, you know, U1 and 1, U2 and 2. So to avoid that, we have to add this extra constraint. Okay. I should write down if. Okay. So this will finish the definition of the constraints, and we choose the solver as the GLPK, and we can specify the n and max degree. So let's run the code with each other. So I've run the first tab. Okay, it is run successfully, and also the second tab is done. Okay, and the third tab is specifying n equal to 10 and max degree is 4. So it takes time to finish the solve statement, because for example, if you have 10 nodes, then 10 multiplied by 9 is telling you how many binary variables. It will be 90 and binary variables. 2 to the power 90 will be the number of combination that you might have. Okay, so and finally I run this. You can get this graph, you can see here. Okay, so initially as you can see here, the degree of the nodes is, the maximum degree is 3. For example, here is 3, here is 3, but if you add that constraint and consider that, then it means that a new tree will be created, and you can see it here. So I run the final tab for you. You can do it as well. So so this way it has to recalculate how they should be connected to each other. So you can see here that the same location of the nodes, but different way of connecting them together. Okay, thank you very much. Okay, this example is referring to the connected tour. So suppose we want to start from one given point. Let's assume its starting point is point 1, and we want to find out how we can travel to different nodes and come back to the same node without creating a loop or passing any of these nodes more than one time. Okay. Now, in order to model that, again, I put a virtual demand on each node, and I put a generation here as well, and then try to supply every demand in the system. And the objective function is defined as the UI multiplied by dij. Uij multiplied by dij. Uij are the binary variables, and the flow will determine from how the production is flowing to the demand points. And also the flow should be less than UI multiplied by a big M. In order to make a connected tour, it means that at each node, let's call it I, there is only one flow going out. And also at each node I, there's only one flow is coming in. Okay, so in this way we can make sure that we have a connected tour. Okay, so let's have a look at the code. We import the required packages, and also we go forward. So you can see here that the model abstract is created, and also we do need to specify the number of nodes. Set I is representing each node, and j is the alias of I. U is a binary variable defined over set I and j. Flow is a real variable. It's always good to specify the bounds for your variable, so I can put a bound for your variable, and I tell Pyomo that it's a non-negative real number, it's a positive one, and variable g is also between 0 and model n, and also the objective function is non-negative real, so we can initialize any variable as well. And also the locations of these nodes are randomly allocated. The second rule is calculating the distances between different nodes for each pair of nodes, and a parameter is defined for that. And also the nodal balance is defined here. For only node 1 it has a G, but the rest of them are only pure loads. The next rule is telling us flow is less than U multiplied by a big number. I chose that big number equal to the number of nodes. So this constraint is defined over I and j. Okay. It's definitely better if we define this rule in a way that it doesn't it's not calculated for the cases where I and j are equal to each other. So let me modify this code for you. Okay, so I put a if here. Okay, so here you can see that if I is not equal to j, then return this. Okay, else else return what? I have to skip that constraint in case that these two are equal to each other. So constraint dot skip. Okay, I hope it's correct. Okay, so I will check it for you next, and then let's have a look at the other code, the other constraint. This constraint is telling us that summation of uij over j should be 1. It means that the outgoing edges should be only 1. And also this one is telling Pyomo to say the incoming edge to each node should be only 1. And the objective function is doing the summation over ui urc multiplied by drc and so on. Okay, so let me run the code. Okay, and this one, okay, it is also correct, and the solver is chosen. I run the it says constraint has no skip. Maybe I have made a mistake the way I wrote the skip. Skip should be capital, I think. How about now? So I run it again and check the result. So I'm waiting for the model to give me the solution. Okay, so here you can see we have a connected tour. Okay, so as you can see, all the nodes are connected to each other, and the degree of each node is 2. So you could write it down in a different way. So instead of writing it as 2 separate constraints like model.c3 and c4, you could say degree of each node should be exactly equal to 2. That should give you the same kind of result. Thank you very much. Example is called the conference allocation. Suppose we are about to organize a conference, and for example, let's say the participants are participating in this event from, let's say, 20 different cities or countries, and but unfortunately, due to some restrictions, they can't all travel to one location, okay, to have the conference right there, okay, and they don't have the communication facilities at every city, okay. So the question is it possible to pick up some specific cities and then connect these cities with a teleconference to each other? Okay, so the question is, how can we choose some specific number of cities for having the teleconference facilities right there, and then connect them together in a way that the traveling costs are minimized? Okay, so let's solve the problem together. Okay, so we want to minimize the traveling time and traveling distances. Okay, so let's define a binary variable like Lij. It means that the travel should happen between I and j, and multiply it by the distance between these two cities. And also there are some other constraints. For example, this one, the summation of Lij over j means that every person living in city I should only travel to one city, okay, so not more than that. And also the number of chosen cities are already specified. Let's call nc. So the summation of ui, which is a binary variable as well, over I will be nc. And finally, let's say ui is telling us if a city I is chosen for having the teleconference facilities or not. Then another constraint should be written here. Let's say Lij should be less than equal to ui plus uj. What does it mean? It means that if a travel is going to happen between I and j, then at least one of them should have the teleconference facilities. Okay, it can't be the case that if none of these cities have teleconference facilities and traveling is happening between them. For example, here you can see that for 20 cities, city number 5, city number 1, and city number 10 are chosen to host the teleconference, but there is no travel happening between 11 and 16, for example. Okay, so this is it. If I have, let me show you some sensitivity analysis. So suppose we have the same number of cities, 20. So all of them are scattered on the plane in the same way, but each case the number of conference facilities are changed. So first of all, only 2 cities are chosen. You can see it here. So the objective function is 1.635. If I increase the number of cities equal to, let's say, 4, so the objective function will even reduce. And if I increase the number again by 6, then it means that the objective function is now lower. And finally, if I choose 8 points, then the objective function is at minimum. So you can see that if we have 20 cities, and if it is possible to choose all of them to have teleconference facilities, then the objective function will become 0 because no traveling is going to happen. Okay, so just have another look at the formulation, and I will run the Python code for you. So here you can see that and this is the Python code. So first of all, I import every required packages. Then we have to write down the required constraints. So n is the number of cities, nc is the number of conference to be allocated, I and j are representing the nodes, u is the binary variable showing that if a city I is chosen for having the teleconference facilities or not. The link is telling that if I and j are connected to each other. It's a binary variable as well. Objective function is also defined. The locations of the nodes are randomly generated. And also, so I want to write down the codes. So the summation of ui over I is equal to nc, and also summation of link ij, the summation over j should be 1. We should keep in mind that j should be different with I. And also this one is telling us model link ij should be less than ui plus uj if I and j are different with each other. And finally, that's the objective function. Objective function is defined this way. So I didn't define a new parameter d to be calculated. I just wrote that expression here. Okay, so you can easily see that how the objective function is defined. Link multiplied by dij, which is an expression like this, and the solver is chosen to be glpk, and the number of cities are 20, and 3 conference centers are considered for this purpose. The model will be created using this line. It means that all the constraints and the associated input data will be fed into the model, and then the chosen solver will solve that created model, and the objective function is given to you. Okay, and this case is solved for 20 cities and 3 conference centers, but you can easily create a loop to change those NC centers and see what is the impact. So I run the code again for you. Since the code is written in a way that every time it is run, the locations of the cities are changed and updated in a random way. So the objective functions are different in every case, but you can see that by increasing the number of cities, the objective function is reducing, see? Okay. And also, sometimes you want to know what's going on inside one of those equations. For example, let me show you one of them. For example, equation 2 here. So it is doing what? It is trying to do the summation Lij, link ij, doing the summation over j should be equal to 1. It means that the outgoing, the travel between each node should be exactly 1, not more than that. So here you can see at the end, for if the starting point is 1, then 1 plus 2 plus 1 plus 3, 1 4, 1 5, 1 6, 1 7 to the end, okay? Though that should be equal to 1. And you can see what's exactly happening inside each constraint. I just put the equation number 2, but you can change the name of equation and specify any other equation that you want. This is definitely useful for doing the debugging and finding out where exactly you might have wrongly coded your constraints. Okay, thank you very much. Okay, this example is called the maximum flow. We want to find out how much is the maximum flow we can have between two specific nodes in a graph. For example, if the amount of product or power or whatever is entering the node 0, and we are expecting that there is no losses is happening in the system. I repeat, it's not an electrical engineering kind of system, but it's a general form. And we want to know if we enter G to the node 0, is it possible to take out G from node 6 or any other nodes without violating the capacity of these lines or these routes? Okay, so in order to do so, we have to write down the balance equation for every node. So as you can see, only one node has generation, which is node 0, for example, in this example, and the rest of them they have no generation, but and no demand, and also only one node has demand, which is node 6. Okay, so and it's equal to G. So we want to know how can we formulate it as a optimization problem in Pyomo. Okay, so here you can see that we import the required packages, and then I create the model, abstract model. This is the set. It is initialized with the range between 0 and 7. So it will be created 0, 1, 2, 3, 4, 5, and 6. J is the alias of that. Flow is telling us how much flow is happening between I and J. It's a positive number. And also the capacity of each route is also specified by parameter cap. G is a variable telling us how much we can inject to one node and extract from the other node. An objective function is defined as G. Okay, so here let me continue. So I have to write down the balancing equation for every node. So the first node, which has generation, is written this way. So if I is 0, this is this way, and if it's the receiving point, this is written this way. But if it's none of any of those two types, then there is no generation, no load, and that's the constraint defined for every node. And also the flow should be always less than the capacity, and the constraint is defined over I and J. The rule is C2. and the objective function is expression model G. So this way you can see that I don't need to define an extra variable called OF. Okay, it doesn't give me anything else, so I can remove it for simplicity, and I choose the solver as the GLPK. So the unknown parameter I haven't discussed it so far is the capacity. So the capacity should be specified in the dat file. So you can see it here. It's a kind of table specifying how much is the capacity between each pair of nodes, and you can see that in this specific example it's not symmetrical, so the capacity between 2 and 1 is 10, but between 1 and 2 is 0. So it's a directed kind of graph. Okay, you can change the numbers if you want and see the impact. So it will read that data file and put it into the Pyomo and ask it to solve it. Okay, so you can see here that I can plot the results and show you what's happening. So I run it and I explain what's happening at each stage. Okay, so the model is solved here and the data is given here. So I want to plot that graph, so I put a circle and connect the connected points, and the capacities are somehow graphically shown here. The routes with higher capacity are specified with thicker kind of lines, and also you can see the objective function is 7. Okay, so this is the maximum amount of energy that is capable of passing from 0 to 6. And there are some useful information regarding the solved example. So just have a look at the this instance.display. We want to find out if our modeling approach is efficient or not. Okay, so so how much is the maximum capacity? It's it was 10 in the data file. Okay, so we could also specify before I explain that, I just have a look at the variables. The variables is flow G, and what else? Objective function is something else. Okay, so there are two main variables, G and flow. So just have a look at the status of each variable. Okay, so as you can see here that we have a variable called 0 and 0. It means that the flow between node 0 and node 0, which is not going to be true because I don't need that kind of variable in my model. Okay, so why is it created? Let's have a look at the model, the way I wrote it. So here you can see that I have a condition that I should be different with J, the same here. So this constraint is not creating the problem for me. This is the one. Okay, so because I am defining it for every pair of I and J. For small problems, it doesn't create that much hassle, but for larger kind of programming, it should be definitely avoided. So let's put a condition here. Let's say if I is not equal to J, then return this, else return constraint dot skip. Okay, so if I run the code again, I hope I avoid that. What happened? Okay, so the problem is solved, but here let me check. So there is no combination of 0 and 0 and 1 and 1 and so on and so on. Okay, So in order to check what is happening here, I have to see this line. Okay, so let's have a look. So it is telling me that it is trying to access one specific component of a flow which doesn't exist. It can be understandable because now let me do this in this way. Okay, so I put it here. If value is bigger than this, then plot it. Okay, I hope this time it resolved the problem. Yeah, very good. And run the last tab and see the results. So you can see here that yeah, it doesn't exist in the model. The stall is now true. It means that it doesn't it's not included in the model. Okay, and it doesn't have any value, as you can see here. And also there is another point that can be considered, and it's the fact that there is no upper bound for the flow. Okay, so it's none. So it's always, as I said before, it's always good to have a bound for your variables. So even if it's not very tight, but at least it's something right there. So if I run the code again and let's run all the tabs and see the results. Okay, so as you can see here, the upper bound of the variable flow is now determined. Okay, so these are the steps that you can follow to improve the way you run. In this example, we want to talk about the graph node coloring problem. So consider this graph. It has a number of nodes that are connected to each other, and from the graph we just know how the nodes are connected to each other, that this is the input data of the problem. Okay, so the question is, if we want to color the nodes in a way that no two adjacent nodes are painted with the same color, how many colors do we need? What is the minimum number of colors that we need? So suppose if we have n nodes in our graph, then if we have n colors, we can easily solve this problem. Okay, but there is a much smarter way to do this. For example, if you look at this graph, you can see by only two colors the nodes are painted in a way that no two adjacent nodes are colored with the same color. So if you look at here, these two have different colors, but this yellow and this yellow one have the same color, but because they are not directly connected to each other, that's fine. So how can we formulate it as an optimization problem? So first of all, we need the input data of the graph. So Lij is 1 if I is connected to j, and Xic is telling us node I is colored with the color C. So we have a set C, it has a range of colors, and I is the set of nodes. So we want to find out an optimal mapping between nodes and the colors. So we want to know which node should take which color. Okay, so Xic is a binary variable, Xjc is the binary variable, I and j are alias with each other, so they are from the same sets, nodes. Summation of these two variables multiplied by Lij less than 1. So if Lij is 0, it means that the constraint can be easily satisfied because 0 is less than 1, it's automatically satisfied, it's inactive. And if Lij is 1, then Xic plus Xjc less than 1. So that constraint is defined over the sets I, j, and c. For every I and j and c, if Lij is 1, then the summation of these two variables should be 1. It means that if two nodes are connected to each other, they cannot get the same color. Okay, And y is the objective function, should be bigger than equal to cxic for every I and c. And the last constraint is telling us that every node should take only one color. So every node, every color can be assigned to only one node. Okay, so let's have a look at the Python code for this purpose. So the Python code is here. I import the required packages. So first of all, matplotlib networks for drawing the graph kind of plots. This is a built-in kind of facility in the networks package to plot the graphs with the given sizes, and also the position of these nodes are determined. And then we will import the Pyomo, matplotlib, numpy, random, and also panda. Okay, and then we construct the model. We assume that the model is an abstract one. N is the number of nodes, I is the set of nodes, J is the same, color is set of colors, the maximum number of colors will be this number of nodes, and L is a parameter showing that if I is connected to J actually, and X and Y are some variables. So X is a binary variable, but Y is a non-negative reals. So we can easily solve that. Let's write down the equation that we need. So you can see here that L multiplied by xic plus xjc less than 1. That constraint is defined over I, J, and color, and that rule should be followed. And then the objective function should be bigger than c multiplied by model xic, and that constraint is defined over I and C, you can see here. And finally, every node should take only one color. That's here, and the objective function is model.y. And the sense is minimization, so we want to find out the minimum number of color required for painting that graph. So since the model is linear, I choose the GLPK solver, and so here we have already created the graph, you can see, and also here we have access to the number of nodes in that graph. So model.n is initialized somehow, and then the instance will be created here. Okay, so let's run the code so far to see what's going on. So I run the whole tabs and I will explain the results. So let's begin from the first tab. So the first tab, the required packages are imported, this second one as well, and the model is created here. It is the instance will be constructed. It means that the L and other constraints are fed into the model, but keep in mind that I have not specified the L yet, so the connectivity matrix is not specified yet. So I have initialized that is equal to 0, so all of them are not connected to each other, but the model is right there, and we have to update the L and feed the right connection matrix to the instance. So for this purpose, what we do is we can easily find out which nodes are connected to which. So for an we create a for loop edge in g.edges. If these two are connected to each other, then instance.lij is equal to 1. Okay, so from nodes, and two nodes are found using these commands. Okay, so, and then what we should do next is let me double check it here. So instance is updated, and L in the instance is updated, and we have already defined it as a mutable parameter. You can see it here, it's a mutable one, so it means that you can update their quantities. And then we can ask the Pyomo to solve it for us. So it is trying to solve the problem. Since it has some binary variables inside the model, it may take time to solve that. And so the model is solved. Okay, you can see that L is printed here. For example, it's not really necessary to print all these, but for checking purpose you can do it. So it means that 1 is connected to 2 and the value has 1, and so on and so on. Okay, and finally you can see here that the graph is colored. Okay, and each XIC has taken the value. So let me show you what's happening here. So here we can see easily that what are the values of XIC. For example, node 1 color 1 is 1. It means that node 1 is colored with color number 1. Node 2 is colored with number 2. Node 3 is colored with the number 1. Node 4 is colored with number 2, and so on and so on. Okay, so and already we had specified each number means which color. Okay, so we should have a list for the columns, and we can choose which color is selected. Okay, and that's it. This problem is referring to the graph edge coloring. So suppose we have a graph, we have a connected graph, and we want to paint the edges in a way that no two edges that have some mutual nodes have the same color. So look at here, look at the node 9. There are 4 edges connected to this node. None of these edges should have the same color. So we want to find out what is the minimum number of required colors to paint this graph. Okay, so let's write down the codes. So here you can see that for every node we should have some limits. So for every I and C we have to write down this constraint. So it is saying that summation of xijc, and the summation is over j, whatever is connected to I, should be less than 1. It means that the summation of all the edges that are connected to one specific node should be less than 1, and this is valid for every I and C. So no two edges have the same color if they are connected to one node. Okay, and the other one is like the previous one, like the node coloring one. So Y is bigger than C, X, I, C, Ij, and C. And also we should say that every edge should take only one color. This is the last equation. Okay, so if I run this simulation, this is what you get. So you can see here that how the graph is colored and the number of required colors are determined. Okay, so let's have a look at the Python code for this problem. Here you can see that first of all we need to import the required packages like matplotlib, networks. Here it's not needed to re-import that. I can remove this one, so because we already have it here. So I create a random regular graph with the degree of 4 for each node, and there are 30 nodes, and I plot it, and then I import the required kind of packages, construct a model. So that model is an abstract model, and it's the number of nodes. As you can see, it is initialized with the number of nodes and the number of edges. I and J are the set of nodes. L is the connection matrix. Color is the color. And also X and Y are two variables. X is defined over I, J, and color. So it means that the color of no edge which is connected between node I and node J, and Y is the objective function. Okay, so in order to solve that, we should create a constraint, saying the first constraint actually. So if I show you that again, so here I write it on this one. Okay, so in order to write it down, I write this expression. So initially the expression is equal to 0. Okay, and for every j in the model J, if j is connected to I, so xi, j, and c is added to the xi, or if lji is 1, then xji will be added to the model, and that expression should be less than equal to 1. Okay, and that constraint is defined over model I and color. And this guy, instead of writing down y bigger than c xi j c, I wrote it this way. I did the summation over all color and I and j if they are connected to each other. And this is why the reason that I'm doing this is that if I define it y bigger than c xi j and c, this means that for every combination of I, j, and c, I have to create a constraint. Okay, and that will hugely increase the size of the model. Okay, but that kind of modeling gives you the same kind of result. And finally, every edge should have only one color. Okay, and finally, the objective function is y, and the model is glpk. We can specify the gap for the mixed integer programming, which I did it here. So I can run these tabs and show you the results. Okay, so first of all, we have to create a graph. Okay, and this one. Okay, so here I have to create the L part and also N. This is one way of creating the data and feeding it into the Pyomo. So I create a dictionary and fill every required parameter in the model. Okay, so I run it again. So it is run, and I here just the model is being fed with the input data. Okay, and the model is solved, and you can see the results here. So the results is telling me that it's showing that IJC and the value of it. So IJC and the value of it is that, so it means that the node between 0 and 17 is colored with the color number 3. Node between 1 and 6 is colored with number 2, and so on and so on. Okay, and you can graphically see what's happening here. Okay, so here you can see that, for example, at node 13, 4 colors are used, and so on. Okay, and that's it for this example. Thank you very much. This example is called the facility allocation. Suppose we are about to allocate some facilities in a network, and each node should have that specific facility, or at least one of its neighbors or connected nodes has that facility. So we want to find out the minimum required number of nodes to allocate these facilities. So here you can see a given graph with, if I'm right, there are 19 number of nodes, and we want to find out what is the minimum required facilities and which one of them are the best one to allocate that facilities. So I define a binary variable called xi, and we want to minimize the summation of that, and for each I, xi plus summation of xj should be bigger than 1, but summation of xj is done in a specific way. Only those j's that are connected to I. So we are doing the summation over the neighbor nodes. Okay, so let's have a look at the code. So here I import the required packages like networks, matplotlib, and these two are required for plotting this graph. So the one random graph is plotted here, and then the other packages are imported here. So since we have already imported that one, it's not needed again. And also I run this one as well. And then I will create the abstract model. N is the number of node, which is initialized with the G node, length of G node. I and J are set representing the nodes. L is the connection matrix. X and Y are the decision variables. Y is actually the objective function as well. X is a binary variable. And this constraint is created, as you can see. Look at this one. If Lij has value equal to 1, then the summation is going to happen. You can see that the model, also the final one, y is bigger than summation of xi. I could say equal to that, but that will give the same results. So in this tab, I am feeding the data into the model. Okay, so I run this. Here I do have the edges in the graph, so I create the lines, and the lines will be fed in that dictionary, which is going to construct the data for me. Okay, and the solver is GLPK because it's a linear kind of programming. And then we can print that. It means that the nodes, there are 7 nodes required for this specific graph, and the chosen nodes are like this. Here you can get some information regarding how the model is solved, is it feasible or not. And finally, the final solution is given here. So you can see that the selected nodes are specified with yellow color. For example, if you look at the node 2, the neighbor node has a facility. Node 7, the same. Node 14, the same. Node 12, the same. So node 16, the same, and so on and so on. Okay? And that's it for this example. Thank you very much. This example is referring to the curve fitting problem. So we do have a set of points on a plane, and we want to find out a second degree expression that approximates the behavior of these points in the best way. So it means that that line should be somehow representing these points. Okay, so the input parameters are the locations of these points. Let's call them xi and yi. And the question is, what are the coefficients of this expression? A, B, C are the decision variables. Okay, so let's have a look at the Python code. Okay, so this is example 26. Okay, so first of all, I import all the required packages. This is an abstract model. So n can be a number of solutions that the number of points that I want to draw a line between them. I is the set that represent each node, and also A, B, C are the variables, and we have a model .of, which is going to be representing the objective function, which is the error of estimation. Okay, so first of all, I create some random points on the plane, and then write down the objective function, which is model A multiplied by x location square plus b dot model x location plus c minus y location. Okay, and a square. It means that I'm trying to find a, b, c in a way that the difference between the line and those points are minimum. The square of that is minimum. And since it's a non-linear programming, I have to use IP opt, and then I'm using the model.n, yeah, for this purpose, and run it. Okay, and the points are here, and the line is through all of them. Okay, and that's it. Thank you. This example is, let's name it the paper company. So suppose we have that black paper, and let's assume the length of these big paper is 1 meter, and we want to create we want to cut these big paper into smaller pieces, and you can see these are the requirements. So piece X has a width of 5, and piece Y has a width of 7, and piece Z has width of 9, and they have the same length of the black one. Okay, so the question is, how should I cut the paper in order to minimize the number of big papers I have to use? For example, let me give you an example. If I want to cut this big paper into and create some X piece, it means that each paper can give me 4 pieces of piece X, yeah, and also it can give me 2 pieces of these red ones, or 2 of these yellow ones. Okay, and there are some parts are lost, yeah. So how should I do that in a way that the number of big papers that I'm using is minimized? Okay, so definitely I have to choose the binary variables. Okay, so I want to know for each piece of paper, let's call it I, how many X I can extract, how many Y I can extract, how many Z I can extract. For example, 1 X, 1 Y, which will be 12. I can't do any more Z because the width of the paper is not big enough. Okay, or what else I could do? I could say 5 and 2 pieces of red. It will be 19. Yeah, it's less than 20. Okay, so 5x plus 7y plus 9zi should be less than ui. Yeah, so it's better to write it down. It's okay, this example is called the paper company. Suppose a paper company should cut its raw papers, which you can see them as the black big papers, into the color ones. And the size of each color paper is known, and also the black one as well. And I want to know how should we optimally cut these big black papers into the color ones. Okay, so let me give you an example. If I only need the X kind of size, it means that each black paper can give me 4 of these green ones, or 2 of these red ones, or 1 green and 2 red, yeah, or 2 yellow ones. Okay, so the width of the paper should be always take into account. So we want to minimize the number of big papers I'm going to cut, and for each given paper, how many X and Y and Z I can extract. So 5X plus 7Y plus 9Z less than 20 UI, and NX, NY and NZ are telling me the required number of each piece. Okay, as you can guess, I have to define them as binary variables. Okay, so let me show you the code. So here I import the required packages I defined as a concrete model, and also you can see here that u is a binary variable, and x and y and z are, let's say, integer non-negative integer variables. Okay, So first rule, 5x plus 7y plus 9z less than equal to 20 ui. And the next rule is specifying how many of x is required. So let's assume that nx is 10, ny is 12, and nz is 5. You could define them as some parameters. It would be much better and professional, but that's fine. And the objective function is summation of I multiplied by ui. I could omit the I multiplication here, but I will show you why I put it here. And also the solver I'm going to use is GLPK because it's linear programming, and the results are found here and everything is calculated here. So for example, by this answer I know that there are 10 big papers are needed. The first one is giving me 1x and 2y, the second one the same, the third one is only using 3 for x, and so on and so on. Okay, let me run the code from the beginning and show you the results again. Okay, this part is executed. Now the program is running the optimization part. But one question is here that how many big papers I should consider for my optimization, because initially before solving the problem I don't know how many papers are needed. So I define a big number at the beginning. Okay, so how can I determine that? By looking at the number of required x, y, and z, I can say this is the maximum number of big papers that might be needed. Okay, so so at the end I know that 10 papers are needed. So let me check something else for you before I finish this example. If I remove this multiplication, what will happen? Guess what? So I run it from the beginning. So I'm waiting for the solver to finish the job. Okay, I just slightly modified the objective function. And I'm waiting for the solver to finish. Okay, so have a look at the results. This is exactly what I wanted to show you. So you can see that it's 1, 3, 5, 7, 8, 9, 10, 13, 14, and 15. Okay, so the objective function is telling me there are 10 pages are needed, exactly the same as before, but it doesn't matter for the solver that which page is being chosen, so the page with higher rank or lower rank. I mean, they are not sequential. You can see here 1, 3, 5, 7, 15, you see. So but if you multiply it by I, it will give you a more kind of clean solution. Okay, thank you very much. Okay, this example is the famous transportation problem. Suppose we have I factories on the left hand side, S1 to S3, and we have J demand points. Let's call them D1 to D4, for example. And the question is how much we can produce from each factory in order to minimize the objective cost, and also knowing that the capacity of each factory is limited, the capacity of each route is limited, and also the demand should be satisfied. Okay, this is a famous transportation problem. We have some factories on the left hand side, and we have, these are the factories, these are the demand points, and we know the demand of each point and the capacity of each factory and the cost of production and the cost of transportation. So the question is, in order to satisfy the demand on the right hand side, how much each factory should produce, and from which route we should transport these products from the factories to the demand in order to satisfy all the constraints. So there are two sections in objective function. So first of all is telling us the transportation cost. It depends on the distance between the nodes and also how much good are being transported from I to J. Hi, this is the transportation problem. In this example, we want to know if we have some factories, let's call them I, and they're running from S1 to S3, and there are some demand points D1 to D4, and the question is how much each factory should produce in order to minimize the objective function, which is the summation of the production cost and the transportation cost. This is the transportation cost and this is the production cost. And also there is another thing that should be satisfied, that is that the capacity of the factories are limited and they should produce between some specific ranges, and also the demand at each point should be satisfied. Okay, so let me talk about the Pyomo code for solving this problem. So first of all, as usual, we have to import the required packages and then define the required sets. I and J are two different sets. It's an abstract model. We have a demand which is defined over J. P min, P max, and costs are the parameters. So and also the distance between different nodes are defined as a parameter. There's a variable x telling us how much good is moving from I from factory I to the demand point J, and it is defined as a real number. We could define it as a positive real, and also it has a bound between 0 and 300, for example. And there are some bounds for the generation side or the production side. You can say model.p is defined over I, is always within this bound. And also how much we are producing is calculated this way: summation of I and J, or summation of model X, model X ij for J in model J. Maybe we can improve it, but we will see. And also this constraint is on the production side, and also this side is ensuring that the demand is satisfied. I intentionally put it bigger than equal to the demand because it's easier for Pyomo to solve it, but it will not produce more than what is needed. Okay, so this term is the production cost, and this term is the transportation cost. So everything is fine here, and also the objective function is this, and we want to minimize that. The model, as you can see, it's a linear programming one, and also we have to specify the data. So as you saw, we have some parameters defined on I. So param over I, 1, 2, 3, p mean, p max, and cost. And if we have other characteristics, we could put it here. And also parameter j, it is defined over 1 to 4, and the demand is specified here, and the parameter distance. The distance between each pair of nodes are given here. Okay, so you have to specify that in your dat file. And if you solve it, let me run the tabs one by one. This one is run, this one is run, and also this one is run. You can see the objective function is calculated here, and if you want to visualize the decision variables, you can do it. So I run this tab. So these are the results. Let's read them. It is telling us that the amount of transportation between production 1 and demand 1 is 0. Production 1 and demand 2 is 0. Production 1 and demand 3 is 300, and so on. You could visually show that as well. So these are the results that are visually shown. You can see the biggest transportation is between 0.1 and demand 3, and the next one is between 2 and demand 1. So if we have a look at that here, it's here. So you see the next big quantity to be transported is from 0.2 to demand number 1. Thank you very much. This example is going to talk about the multi-objective decision making, and we are about to find out the Pareto optimal front. So far, the examples that we have analyzed with each other are all referring to single objectives. So we had one objective function that we wanted to minimize it or maximize it and find out the optimal decisions variables. And as you can see on this plot, suppose we want to maximize two different objective functions simultaneously, and there are some solutions found as you can see on this graph. So if I show you another solution on this space, the blue one, the dark blue one. So if I look at these solutions, there are 5 solutions you can see here now. If I want to compare these solutions together, I can say that this solution is better than the dark one because it is better than the dark one in terms of OF1 and OF2, and it has better solution in every aspect. Okay, and also the white one has bigger OF1 and OF2, but the green one has a bigger OF2 but smaller OF1. So I can say that this solution can be dominated by this blue one and the white one. So if there is any solution that can dominate this guy, then we have to eliminate that. Another solution, consider this one. Now if I want to compare the red one and the orange one, which one is dominating one? the red one. The red one is dominating the orange one. Okay, so now I hope you understand the meaning of domination. So if I ignore these two new solutions that I showed you and just look at these four, these solutions are not better than each other in every aspect. So if I improve one objective function, I'm deteriorating the other one. So the question is, how can I, if I have a problem with two different objective functions, how can I find out these Pareto optimal solutions? So but before I proceed to the coding and everything else, I want to ask you, why do we need multi-objective optimizations? So can we combine the objective functions and then solve the augmented one in one shot? For example, let me give you another example. So you want to build a production plant, and there are some costs associated with that construction. There are some operating costs, there are some investment costs. So you can easily do the summation and then ask your decision making tool to find out the best decision for you. Okay, but sometimes the objective functions cannot be added together. They are from different dimensions. For example, one of them is environmental, for example, pollutions, and the other one is cost. Some people say that the environmental aspects can be translated into cost. Sometimes it's true, sometimes it's not. Or there are some other aspects, for example, the beauty of something and the cost of something, you know. So these two cannot be added together because the dimensions are different. Or sometimes these are costs, but both of the objective functions are cost or benefits or whatever, financial. But the size of each is completely different with the other one. So the order of magnitude is not at the same level. So optimizing one of them is not putting any effect on the other one, you know. And sometimes the objective functions are the same. For example, they are both cost, but two different people are going to pay them. So adding them together and minimizing the total cost is not always beneficial for both. Okay, so we have to find out some set of solutions, some set of non-dominated solutions, and give them to the decision maker and ask them to choose. And there is another thing. If we go with the weighted sum approach and add the different objective functions using different weights, then we will find out just one objective function and one set of decision variables. Okay, and what happens if that weighting factors change? So we have to run the optimization again. Okay, but now we want to find out the set of solutions, as you can see here, those that are connected with dashed lines, in a way that if your weighting factor change, you can change your solution. It's not needed to run the program again. And also you can see that if you move toward any of those objective functions, what will happen to the other one. So if I am at the orange solution, if I want to go to the blue one, for example, improve it in terms of OF2, I want to increase the OF2. This is how much I will lose in terms of OF1. Okay, so for simplicity, consider this very easy example. There are two constraints. OF1 is something, OF2 is something else, and the range of variation for x1 and x2 are also specified. Okay, so let's have a look at the Python code. I import the required packages. Sometimes some of these packages are not really necessary, but there's no harm if you keep them right there because maybe you need them in the during your coding. So I specify the range bounds of x1 and x2. You can see it here. They are both non-negative reals. And also there are two objective functions, OF1, OF2. They are defined as variables. And also equation 1 is something. Equation 2, I will explain it later. And equation 3 is the other equation. So what is equation 2? Equation 2 is telling us that OF2 is less than something. Okay. So in order to solve that problem, just let me show you something else on the slides and then come back to the points. So if you look at this graph, and if I want to, for example, maximize the OF1, what will happen? What is the obvious solution for that? The obvious solution is here, okay? But, and every time you just maximize the OF1, which is the capability of the Pyomo package, you can only maximize or minimize one objective function, okay, at a time. And if you want to maximize OF1, this is the solution that you will get, okay? But in order to be able to not trapping it here, we add another constraint for OF2. I can say OF2 should be bigger than something, or smaller than something, and then solve the problem. So I change that limit for OF2 and then try to optimize the other one. I could do it for the other objective function, the OF1, and I could say, okay, the minimum value of OF1 or maximum value of OF1 is something. Now optimize the other objective function. But how can I write it down in Pyomo? So this is the constraint I was talking about. So I will limit the OF to less than something, and I will change that limit, okay, iteratively, and ask the Pyomo to solve it. So as you can see here, it's strange. I do have more than one objective function. That's fine in the definition phase. But when I want to solve that, I have to deactivate one of them, okay? So I put a limit for OF2 and I deactivate objective 2, okay? Pay full attention here. And then I ask the Pyomo to solve it. So what objective is being optimized? This is the active objective, the objective 1, which is OF1. So it is solved. In this way, the maximum value of OF1 is found, okay? And how much is the epsilon at the beginning? It's a very big number, you see. So actually there is no limit happening here. But next time I will deactivate objective 1 and keep the objective 2 activated, and then resolve the problem again. So look at the objective functions. The first time the objective function 1 is its maximum value. Second time objective function 2 has its maximum value, okay? So the range of that Pareto optimal is found, and the x1 and x2 are found. But how should I continue? I have to do something about that limit I already specified here, the epsilon, okay? So if I am talking about the OF2, I should look at the variation range of OF2. It is changing between 0.2 to 9.58. So I can say it can start from this quantity and go down up to here, and then try to optimize the other objective function, okay? So look at here. At each point, I write down a for loop, and at each iteration, I am updating the value of the epsilon. So at the first iteration, it is OF minimum OF1, okay? And at the final one, it becomes a maximum OF, okay? So in this way, when I solve the problem and optimize it, I can easily find out the value for the other objective function. So if you can see here, I am starting from 0.2, and little by little I'm increasing this epsilon, you see? and try to optimize the other objective function. Okay. And if you want to graphically show it, you can see it here. Okay. So the number of points depends on the how many steps you have specified for your programming. Okay. And that's it. Thank you very much. If you remember the transportation example, and in that specific example, we decided how much item should be sent from supplier I to the demand point J, and the demand at different points are constant. So now we want to expand that specific example and make it dynamic. When we talk about the dynamic kind of modeling, we mean that some decision variables have time index, means T. So again, we import the required packages, for example, Pyomo, NumPy, and then we need to define an abstract model. I is the set of the suppliers, J is the set of the demand, and T is the set of the time steps. And as I have already explained, the demand is a parameter which is defined over the node J. Pmin, Pmax are the set of supplier constraints that specify the minimum and maximum capacity of the suppliers, and also the cost of supplier I. And also we have added a new parameter called pattern. The pattern is going to define how demand is changing, and it does have an index T, so it is defined over the model.t. And also the distance is also the parameter which is stating the distance between the supplier I and the demand J, and it is defined over the real numbers. And decision variable X, which was telling us how much item are being sent from the supplier I to the demand J, it also has a T index now. Okay, so let's continue. The variable P was telling us how much each supplier is supplying, no matter it is being sent to which demand points. The P bounds are, this is a function which we have already defined it in order to specify the bounds of my variables. Okay, so if we continue, we do need a rule C1. That rule is telling us how much it is going out of supplier I at time step T. Okay, so the summation of model.x Tij for all the J's to all the demands that I'm sending the items, and which should be equal to model.p over T and I. So as you can easily see that this specific expression is defined over T and I. That's why my function is defined over T and I. And for the same reason, when I want to define my constraint C1, I have to define it over model T, model I, and the rule is rule C1. Okay, so next constraint is telling us what? It is telling us that whatever is reached to the demand point J at time T, so the variation of the whole demand is modeled this way. So a constant number multiplied by something which is changing with time. So the summation of the model X for every I in the model I. So it means that whatever is being sent from different suppliers, that demand should be bigger than equal to the quantity of that demand at time T. And this means, and actually if you look at this constraint, it is defined over T and J. There is no I is left in this expression because we have done the summation over I. Okay, so since that expression is defined over J and T, that means that this should have T and J here, and the order of them should be exactly the same as the constraint model T and J here. Okay, and finally the objective function is somehow similar to the previous one, means that the summation of the operating cost P multiplied by the cost of the production over summation over all I and all T, plus the summation of xtij multiplied by the distance, which is also telling us how much cost is happening, and do the summation over I, J, and T. Okay, so actually when we run the objective function here. That should be very easy, because the model .of, it is a variable that is telling me how much is my overall cost, and the sense of the optimization is minimized. Okay, now what we need to change compared to the let's say static kind of version of the transportation problem is to update my dat file. So the only thing that I need to change is giving and providing the Pyomo the pattern of the demand. It is assuming that it has only 6 time steps, 1 2 3 4 5 6, and the pattern of the demand is also specified here. And I change the name of the dat file and I call it here. So let me run the code. So first tab, second tab, third tab. So now the problem is solved and the objective function is found. Okay, and if I want to see the results of the objective optimization problem, you can easily see that at time t1 the values of the suppliers are specified here, 84, 84, 20, and time 2 and 3, and so on and so on. So for the time t4, when the coefficient of the pattern is 1, we should get exactly the same kind of results as we did in the static case. So I will show it to you here. So at time t1, which is the equal to demand here, the supplier 1 is 300, 620, supplier 2, and supplier 3 is 20. So let's get back to my example, 300, 620, and 20. And this objective function is the summation of the all decision variable and the cost associated with them for the whole time horizon. Okay, and there is no drawing for this specific example, but if you want, you can do it easily. Okay, that's it for this lecture.